Good morning, everybody. My name is Hans van Winkel. I will chair the first session. So it's an AGB conference, but now we leave the safety of the AGB to go to more adventurous routes. And we start with Devika, who will tell us more about post-AGB stars. Please.
Hello, everyone, and good morning. Thank you all for showing up. I know it was incredibly difficult for some of you, but I appreciate the attendance. And thanks to all of the organizers, in particular Claudia, for superbly leading this conference and bringing back the series, particularly in Chile. And thanks to the SOC for inviting me to give this talk on post-AGB stars. It is my pleasure to speak to you about it and give you some of the recent highlights. It was a difficult choice. I really had to pick and choose which ones I want to talk about, but I decided to go with something that is quite exciting to me and quite recent as well. So, long list of postdocs, collaborators, and students, all of whom have contributed excellently to a lot of the work in the post-AGB realm. So Amanda showed this HR diagram by Herwig when she started to focus on the AGB phase. And today we're going to be focusing mainly on the post-AGB phase, which is a very brief and transient phase of evolution. So you're looking at about few thousands to 10,000 years, which essentially means that post-AGB stars are very rare. There's still a population, so for every post-AGB star, you're expecting about 1,000 AGB stars. So essentially, it's just a very rare sample. However, they're exquisite tracers of evolution, nucleosynthesis, what happens to the star before the AGB phase, and how stars eventually evolve into their deaths. So I like to use the word exquisite simply because it is really a phase where you can observe the star surface as well as the circumstellar dust and also really see the differences between what single evolution and binary evolution can do. I thought I'd like to start with the discovery of these objects because I said they were pretty rare. And the main clue was the fact that they've got very large infrared excesses. So the discovery of post-AGB stars started way back in the 1980s, looking for catalogs that had infrared excesses. But there's a small problem with that, because if you look at this color plot here, which uses the Spitzer colors, there's a lot of stars that have infrared excesses. So whilst you could use infrared colors to make a primary selection, what this plot really indicates in the different colors is spectroscopy added together with photometry. So the minute you have a selection that is done on photometry and then you bring in spectroscopic classification, you can easily weed out quasars, PNE, background galaxies, and so on. But what you're still struggling to weed out is the young stellar objects. So post-AGB stars and young stellar objects, photometrically and in terms of stellar spectra structures, look very similar. However, we've devised a way in terms of stellar parameters, if you have surface gravities and metallicities, both of which, if you work with spectra, you'll know they're quite hard to determine and they've got large uncertainties. But nevertheless, we were able to come up with quite a strong catalog of post-AGB stars in the galaxy, LMC, and SMC. The surveys are far from complete, so the talks a few days ago on the JWST catalog is definitely worth revisiting and searching for more candidates systematically, which is something on the to-do list. So very quickly, single post-AGB stars, and what's unique about them is this very double-peaked SED, which also means that you get to observe both the star, the stellar surface in terms of its chemistry, in terms of its orbital properties, if it's a binary but not yet, and also the dust. And the single post-AGB stars are really forensic laboratories for AGB nucleosynthesis, dust evolution, and Amanda kind of referred to this. And we've done a lot of work on using abundances of single post-AGB stars to constrain stellar evolution models, S process, I process, dust evolution, together with the group in Monash and also in ENAF, that's Paulo Ventura's group as well. I won't be talking about that today. I will instead continue on the theme of what we've been talking about the last few sessions, which is binarity and complex atmospheres that come as a consequence of binarity. So just a very quick recap. So for binary post-AGB stars, the SED types are typically a little bit more different. So what you see is the star, but you also see a broad onset of an infrared excess, which is sort of indicative of a stable circumbinary disk. Now, the circumbinary disk detection first came from the SEDs and observational studies, but later the group of Valentin Buharabal was able to confirm the Keplerian nature and the stability of the disk using the ALMA CO maps. So how do these disks form? That is pretty much the holy grail, and we still don't quite understand. We believe that it is some sort of stable mass transfer that is sort of somehow avoiding a common envelope and resulting in the circumbinary disk surrounding the post-AGB binary system. Now, what I will do for the rest of this talk is I will sort of try and answer a few of the key questions technically, looking at binary evolution, disk binary interactions, and one of the recent topics that's emerged, which is second generation planet formation, which we're doing a lot of work from Macquarie University and also with collaborators in Europe, with Hans, Javier, and also other collaborators in Australia. So the outline of my talk will be focusing on observations that point to the binary interaction that results in post-AGB systems, the second generation protoplanetary disks, and why do we call them that, and why do we think that there are potential signatures, and what theoretical planet formation mechanisms are we looking at to kind of bring this home. So the outline for the next couple of minutes that I have is going to be setting the stage for post-AGB binaries and kind of posing the analogy between post-AGB binaries with circumbinary disks and YSOs with protoplanetary disks, and finally our approach into bringing the entire key questions together. So very quickly, for those of you who are still sort of trying to understand this complex system, there's the post-AGB star, which is our primary, which was an AGB star before. The companion is typically a main sequence, and we know this from orbital analysis, which is quite extensively done for a lot of the post-AGB binaries in the galaxy, and I'll show you some results in a bit. And then we've got this extended circumbinary disk with the inner rims sitting at somewhat sublimation temperature. Now, we've also got a set of outflows, low velocity outflows that we like to be posh and call jets, emerging from somewhere in the central stellar system. So it's quite a complex setup, and in the rest of the remaining talks, we'll have a lot of us talk about each of these individual components. In terms of analogies, you can see on my right-hand side, I have a schematic of a protoplanetary disk around a young stellar object by Doulemond. And on the left-hand side, I have the schematic of the post-AGB binary system. And you can see that the similarities are really quite striking. The fact that the post-AGB stars are much more luminous means that your inner rim is pushed further away, so you can see that the scales of the disks are a bit different. However, when we do model post-AGB disks, we sort of find that the models that are based on the YSOs, the passive irradiated disks that come from Doulemond and Monnier, really fit the image reconstruction and the high angular resolution imaging data that we have. So we're quite surprised and positively happy that the disk structure for the YSO protoplanetary disks and also the post-AGB circumbinary disks are very similar. Now, I'd like to take you through some more analogies. So what I have here is an HST NICMOS image of HARO 65b, which is a protoplanetary disk around a YSO. And here's AR-PUP, which is sphere VLT imaging, one of the first sphere VLT imagings done for a post-AGB binary system. And you can see that the similarity, again, is very, very striking. So you've got the disks and you've got the central stars. Of course, these disks are very diverse, and I'll sort of zoom into the structure through multi-wavelength, multi-techniques. But just to show that Bensti et al. In 2022 did a collage of protoplanetary disks, and they saw quite a large diversity. And we've actually seen a very similar diversity with the work that Katya will talk about, which is based on the sphere imaging for our post-AGB disks. So a lot of these similarities keep emerging, and in fact, the work by Steve and me in 2019 was quite interesting. It happened pretty much in Chile. I was in Paranal for an observing run with Pioneer, I think it was, and Steve, who is from the young stellar community, was my support observer. So we were talking about these disks, and he said suddenly, hey, they're so similar to YSO disks. Why don't we do a sphere imaging program for this? And I said, well, okay, let's do it. And that's kind of how the entire second generation protoplanetary disk sort of a quest began. And a while later, it's taking off quite well. So I quickly take you to what the group has done in terms of understanding these post-AGB binary systems. And it's quite a multi-wavelength, multi-technique approach. So to study the whole system, to start off with, we've got SED analysis. We then study the central star and the binary using optical infrared spectroscopy, both snapshot and time series. Max will present some results on this. The H-alpha time series talks a lot about the jets. Hans will talk about that. Infrared astronomy gives you the imaging morphology of the inner disk structure. We have Akke and Tone who will talk about it. And then we've got radio interferometry giving quite a lot of results on the whole system, starting from the midplane to the outer parts of the disks. We've got some results from our own group and also the group of Javier. And finally, we've got high angular resolution imaging, sort of exploring the outer surface of these disks, the extended structure, and Katya's talk will focus on that. Parallelly, we've also got my PhD student, Ali, who is working on analytical mechanisms for second generation planet formation, which he's not here, but I will probably present some of his results. So very quickly on the SED analysis, I've showed you SEDs, but I'm just going to touch on a few highlights to kind of bring this review together. And the main result I want to present is that the post-AGB disk SEDs, based on work by Jacques Kluska, who unfortunately had to leave academia, has shown that the SEDs are quite diverse and are classified into three subclasses: full disks, transition disks, and faint disks. I think the one takeaway message from this slide would be that the full disks have inner rims, as I said, sitting at sublimation radius. However, for the transition disks, we find that the inner rims are 6 to 7 AU away, so 3 to 4 times away from the sublimation radius, so at 12 AU or so, which kind of brings in the explanation that there must be something that is causing a cavity of some sort, and we think that that could be a planetesimal or a planet of some sort. So the other question to ask here, apologies, is also how do the three disks actually link and how do they evolve? Do full disks evolve into transition disks or evolve into faint disks? Because faint disks have, as I've noted here, they're quite dust poor, or the dust is settled in the midplane. We don't know the answer to this yet because we don't have a lot of ALMA continuum data, which we're sort of fishing for. So if you ever read our TAG proposals, please make sure you rank it very highly. So this question is very interesting to us, and so far what we find is that full and transition disks probably evolve slightly differently, but eventually evolve, or the end game for both of them is the faint disk type, but Max will elaborate more on that. Now, Mercator, we've heard about this quite a lot, and there's a lot of orbital studies done based on the time series data. So I will probably just like to highlight a few of the results because I've had people ask me. So the companions for these post-AGB binaries are expected to be main sequence stars peaking at about 1 solar mass, but there is a little bit of a distribution, as you can see from this plot of number versus companion mass on the x-axis. And this is quite an interesting plot that has caught a lot of our attentions for a long time. And this basically shows the eccentricity versus orbital period. And you can see that we've shown it in terms of luminosity. So there's no real correlation with high luminosity or low luminosity. And we've also shown it in terms of the different disk types. And we find that there's no real correlation there either. Now, a lot of the population synthesis models struggle to reproduce the orbital periods and the eccentricities you see in these systems, and that is shown nicely in this particular plot where we show the observational orbital periods and then what is predicted by population synthesis models. However, recent work by Kasper Molzer et al. Have shown that for the low luminosity post-AGB, or rather the post-RGB objects, the orbital periods follow the luminosity. However, explaining the eccentricity or the increased eccentricity is still quite difficult because you do expect that you circularize the orbits eventually, but what we see is the orbits do not get circularized and we have systems with quite high eccentricities. So yes, stable mass transfer is probably the way to go, but something else is needed to kind of have these high eccentricities that we're seeing in these systems. Moving very briefly forward, because I do want to sort of go on to the second generation planet formation, which is sort of my pet peeve. So the chemistry of these post-AGB binary stars are quite different to what you'd expect from single stars, the S process, CNO, yada, yada. So what we do find is we find a very interesting depletion trend. So here's a typical abundance plot with condensation temperature on the x-axis, and we find that there is an underabundance of refractory elements that have high condensation temperatures, and you only see the stellar surface with volatile elements. And if you look at the infrared, and I've compared it with YSO's Comet, the ISM, there's this very striking similarity between a lot of the infrared spectra, particularly the 10.3 micron phosphrite silicate feature, which really shows that the disks have silicate grains that really help in the processing and the crystallinity and increasing the lifetime as well of the disks. Now, depletion itself is quite interesting, and I particularly mention this because I said there's different classes of disks, the full, transition, and faint, and we also see the efficiency of depletion to be quite different. Now, we don't necessarily find a trend. It's all sort of all over the place, but this is something that Max will elaborate on in his talk. So, when we saw depletion in these systems, it was quite common, quite obvious for us to compare to protoplanetary systems. And in the PPD community, what they find is they find similar depletion trends, not as amplified as us, and I'll show you a plot in a second. But the work by Britton et al. Have shown that in order to explain their depletion mechanism, what they have to assume is some sort of a pressure bump. So you have a planet that creates a pressure bump, and that pressure bump holds on to the dust, and therefore you kind of accrete only the clean gas onto the surface. Now, the fact that we see depletion quite strongly in our circumbinary disks around post-AGB stars or the post-AGB surfaces is another strong indication of the possible second-generation protoplanetary disk nature for our systems. And here's the comparison I promised, which is the comparison of the depletion trend in the ISM in young stellar objects. It's not as large, but there still is a depletion trend, and in the post-RGB, AGB binaries. So this is a very strong indication of some similarities between the two classes. Now, moving quickly forward, we'll have two talks on interferometric data by Tone and Akka today, so I won't talk much on it. But what I'd like to stress here is that interferometric data has really shown us the structure and morphology of the inner rims of these objects. There's been a lot of complexities, and I'll let Tone and Akka talk about it. But in this particular case, we've been able to confirm, starting from work with MIDI, Pioneer, and so on, that for some of the systems, especially the full disks, the inner rim really sits at sublimation radius. Now, Akka might tell you different, that for the transition disks, the inner rim sits, as I said before, there's a large cavity and it sits a little bit more further away. So interferometric data has helped, particularly the inspiring project, which again was led by Jacques. This has really helped us to understand what is the structure, and can we detect secondary companions? And also, when we do have the mosaic with respect to your sphere and ALMA, it all starts to fit quite nicely. But I'll leave this for Akka's and Tone's talk. All right, so moving briefly forward, in my last 5 minutes, I have two more sections I'd like to go through. So the last part of it is the extended disk structure, as I promised, with imaging. So we've also included, outside of interferometric imaging, we've included polarimetric and direct imaging. And what this gives you is, it gives you the outer extended structure of the disk. So we see the inner part, and then now we're looking at sort of the outer extended structure. Now here's it's our outreach kind of an image, but it nicely puts together the diversity we see in the morphology of the sample of the full and transition disks. We see elliptical disks in terms of their morphology. We see rings and arcs, asymmetries, and so there's a big diversity that we see in the external disk structure for our systems. So this data is essentially from Sphere on the VLT using both the Zimpole and the Iridis cameras. I wanted to present just one particular object just to kind of focus on the highlights, and Katja will then talk more about it. So this is going back to Iris 08, which is one of our poster child full disk systems. And I showed the images from the three different bands, V, I, and H. What you can see in the H band is you have quite a lot of extended dust, but if you look at the V and I bands, you've got a more elliptical structure. Now, if you remember the Iris 08's near infrared interferometric data, it was a nice spherical ring, but when you come to Sphere, you see more of an elliptical shape. Now, we think that there could be a few reasons for this, but a possible reason, and Katja will elaborate on that, could be that the fact that they've got similar brightnesses. It could be that you've got a change in inclination, and we measure that. So between the two bands or the three bands, we have different inclination values. And the fact that you've got a difference in structure and this extended dust, if it's not coming directly from like shadowing or so, it could essentially point to a bit of a warp in the disk. So you can see that we're really bringing together quite a lot of morphological features in these disks per se. I'll quickly touch upon only this plot because I don't have time to go into this. But what we've done is taking the polarized intensity with respect to the total unpolarized intensity, and we've compared it for post-AGB stars Iris 08 together with all of the rest of the YSO objects. And we find that post-AGB systems show relative polarized brightness very similar to the brightest PPDs. And I'll tell you in a minute what that means after showing you this color, which is this index over here. And you can see here that once again, Iris 08, which is our post-AGB star, sits again not so far away from a lot of the PPD systems. And they have similar gray colors, indicating that we see dust aggregates instead of single monomers, talking about the structure and composition and the similarity of the two disks between your YSOs and your post-AGBs. So I'll probably have to skip this slide. This is work from my master's student supervised by Katya and I, and we've got time epoch sphere data, which essentially corroborates our results, but also sometimes shows a difference in features. You can see we don't necessarily see that, but that's to do with the binary motion, but I'll have to skip that for now. Very quickly and interestingly, this is our latest results, and Max is working on this after his PhD has finished, and he's sort of taken this up, and we're very excited. So I guess Javier will talk a lot of the radio interferometry, but here I'd like to show the first almost sharpest view that we've managed to get on IRIS-08. The data is definitely limiting us, but we've got observations for 3 epochs, and here's your continuum, so not so boring in our opinion. And then once you remove the spherically symmetric model, what you can see is some sort of asymmetries and discontinuities. And if you compare that with sphere, it's a little bit harder for us to do. The young star community does this a lot because they have cavities. So with ALMA, you're really looking at the mid-plane, as many of you know, and with sphere, you're looking at the surface. So if you had gaps or cavities and you compared the sphere data and the ALMA data, that gap and cavity will appear in both of the data sets. Now, for us, it's a little bit more harder because it's not really a gap, but there's something like a asymmetry or some sort of a pressure bump. We're still sort of looking at it, preliminary results, but this is quite exciting for us. And with the ALMA large program we're hoping to go in for, we're aiming to collect a little bit more on the continuum. So I'll start summarizing. Here's a list of similarities and differences. A small mistake here. It's about 20 to 40 AU of the scale height, but I know it's a lot to take. But in reality, whilst there's a lot of similarities, I'd like to point out the differences, which is the disk mass and definitely the disk lifetime. So these are the key differences, which then makes the question of second generation planet formation quite tricky. So as I said, here's Ali, my PhD student, together with Ursula DeMarco. And what we're doing through his PhD and the work that he's leading is he's trying to explore analytical prescriptions for second generation planet formation. So we've done gravitational instabilities and we're exploring core accretion at this moment in time. What we find with gravitational instability, and the paper's just been published, you can take it from this QR code, is that in general, post-AGB disks are too hot and too light to become gravitationally unstable. So if you are making second-generation planets, it's not likely to be through gravitational instability. With core accretion, however, we're finding a slightly more positive results, provided a streaming instability does take place. It's a bit too much, so I think I'll stop here for now, but I'm very happy to talk more about this to anyone who's interested. So future work is in this particular direction. As I said, post-AGB binaries have many key questions. The post-AGB singles have, but for the second generation planet formation, our agenda is very clear, and we're all very excited also with the new upcoming facilities. And on the similar vein, we've just been awarded a lot of sphere time, where the idea, something that was sitting in my desk for quite a long time, was really to explore and understand whether evolved stars across the HR diagram also are showing signatures of possible, similar to what we see in post-AGB and YSO disks. I'll stop with that. Thank you very much.
Thank you very much. Questions?
Hey, Devika, thanks for a very, very nice talk. I have just 2 questions of things I do not understand and that you might have tried to explain, but I still didn't get it. How can you explain me again the potential transition, or the potential mechanism that causes a transition between your different disks, from this full disk towards this faint disks, and then it was at the beginning of your talk?
Yeah, so that's actually a really good question, and we don't have the answer to that. So that's a question that really also comes from understanding how these disks are formed. So we started off thinking there could be, disks always dissipate with time, so there could be a possibility because of the fact that the inner rim in these systems are quite further away. There could be a possibility that it's evolving in this sense, but we've done a few correlations in terms of the temperature of the stellar star, of the stellar surface of these systems, and they don't correlate. So the transition disks are not necessarily more evolved than full disks. So that made us think that there must be different ways of forming the full and transition disks, which we don't quite understand, because if you look at the simulations from Ursula DeMarco's group, they're actually struggling to make a stable disk. So making a disk is very hard. But we now think, and Max might talk a little bit about this, that these two systems probably evolve differently in a sense, but they are likely to then end up with the disk dissipating away. But there's also some small issues with that. So essentially, we don't have the answer to that just yet. So we don't know, I would say.
And can I add a second question of things I don't understand?
Sure.
Chairman? Yes,
If this,
Chairman?
yeah.
Can you explain me again how this pressure bump works in terms of accretion or not accretion of your
Yeah.
gas versus dust? What I didn't grasp really the
Yeah.
physics there.
So again, this is something that was put forward for explaining the depletion that is seen in young stars. And I believe what they find there is, because you have planets in PPDs, and that's quite well known, you are likely to get pressure bumps because of the asymmetries and gaps. And when you have a pressure bump, you sort of land up with your dust separating from your gas because of the density difference. And I think that's what is tried to explain here. So you've got a pressure gradient resulting in some sort of a particle trap. So you've trapped your dust here, and then you've got the dust trapped away, and then you accrete the clean gas onto the star. So I think it's probably the pressure bump is only caused if you have a planet already in the architecture. But yeah,
But then I
we
think
can
it's later on, eh?
we should
yeah, let's talk about it.
yeah, we can talk about it
not
during
entirely-
coffee.
yeah.
Thanks very much. And we
Everyone?
So next talk is already introduced, and it will be by Katja. Nice talk.
Good morning. Yeah. So my name is Katarina Andrić. I'm postdoc working with Devika at Macquarie University, and I'm going to continue the same topics that Devika just introduced. And but I'm going to focus more on the disk structure. So just as a quick recap, we have a binary post-AGB system. We have a primary star, which is a post-AGB star in a quite quick transition between the AGB and planetary nebula stage. We have a main sequence star as a companion, and we have quite stable disk in a Keplerian rotation. So my research mostly focuses on the extended disk structure and the surface layers of these disks. And we can investigate what is the morphology of those surface layers and what is the dust composition by using direct high-resolution imaging and polarimetry. And this is one of the first images of post-AGB disks. And here the orientation of the system is such that the disk midplane partially blocks the central binary star, and we can see the disk structure quite clearly. But it's not always the case. And if the system orientation is different, trying to image the post-AGB disk becomes quite similar to trying to image a firefly next to the lighthouse. So we need to somehow suppress or block the direct light from the central binary star to resolve the disk surface. To do this, we use the real T-sphere instrument in polarimetric mode, because we cannot really use the chronographic mask. The size of post-AGB circumbinary disks are typically up to 1 arcsecond. So when we use chronographic mask, it would block most of the light that we actually want to see. So that's why we're using polarimetric imaging mode. So when the light is scattered on the disk surface and imaging with sphere gives you direct access to the scattered light, the way it's scattered and the distribution of intensity would be a bit different when depending on the size of the grains. So if you have the grains smaller than the wavelengths you're observing in, the scattering will be isotropic, so you see more or less similar intensity along the disk surface. However, if you have grains comparable with the wavelengths of observation or larger, there will be a dominant or more effective scattering towards the observer. So the side of the disk that is closer to you will appear brighter than the backside. And the direct light from the star is typically unpolarized. But when the light is scattered on the dust in the disk surface, it became polarized. So we can use this effect to separate light from the direct light from the star from the light that was scattered on the disk surface. And if we assume that the light was only scattered once on the dust grain and the disk is not significantly inclined, we expect that the polarization will be oriented azimutally with respect to the central star. So in this way, we can also separate light that comes for sure from the disk, from the scattering on the disk surface, and any noise or calibrational effects that are coming from interstellar medium and instrument itself. So all of the images I'm gonna show further in this talk are azimutally polarized images. So it's for sure intensity that we have from the disk, or in some cases, the total polarized intensity, which is a bit more noisy, but also has a bit more signal, which is critical for quite faint disks. To accurately and consistently reduce and analyze the data for our targets, barely resolved targets, we combine the existing sphere data reduction software, such as ERDAP, Sphere DC, and SZ, and also our custom pipeline, OPEL, which includes the additional correction for the instrumental effects close to the central star, as well as correction of unresolved polarization, and it is tailored towards barely resolved targets and disks in particular. However, it can also be used for other circumstellar environments. So now coming to our observation results, the target sample consists of 11 post-AGB disks, and they were selected in a way so they form a representative sample with a quite wide range of temperature for the central star, orbital period, inclination, and also range of chemical composition. So what is particularly great about the sphere, it has two cameras, ZIMPL and IRDIS, which allows us to observe both in optical and near-infrared. And also ZIMPL camera allows to do simultaneous observations in two wavelengths. So then we eliminate any variation in our signal due to atmospheric turbulence, and any changes in the brightness distribution of the disk or the morphology comes directly from the disk physics and not some instrumentally introduced effects or atmospheric effects. Devika has already showed this particular set of images. So here you can see that we have a quite diverse set of morphologies we see for post-AGB circumbinary disks. Some of the disks show quite clear elliptical surface structure, while others shows rings, arcs, scattering from the backside of the disk, and also very asymmetric structure, pointing that we don't have just a nice smooth disk, we have a bunch of very complex morphologies that we still need to understand what is causing them and what is the underlying physics. We also have multi-wavelengths data. So we combine the data in both optical and near-infrared, and as you can see, the results are quite consistent across wavelengths, but there are some systems that show a bit of variation and appear more extended towards longer wavelengths. This can be attributed just to the fact that the dust opacity decreases with the wavelengths, and we can probe a bit lower disk surfaces. But also multi-wavelengths data allows us to directly measure what is disk polarized brightness, what is the polarimetric color of the disk, and investigate what is the underlying dust properties for the system. So we found that post-AGB disks appear quite significantly bright in polarimetry, so with polarized intensities up to 2% of the total intensity of the system, and colors for the system are quite gray or slightly blue, so the polarized intensity doesn't change much with the wavelengths. This, together with the presence of forward scattering peak in the polarized intensity for some of the system, points towards the presence of quite large dust grains around submicron or micron size, and also porous aggregates. However, to accurately confirm this, we need to do the modeling. We're also able to directly measure the scale height for two of our systems. So for the left one, we measure the height of the secondary ring. So we resolve the second ring, and we see that the center is slightly shifted from the position of the binary, which is due to the projectional effects. So we are able to estimate how far it is from the midplane to get this projectional effect. And for the system on the right, we directly resolve the disk midplane so we can measure its thickness directly. Devika has already mentioned the RS-8 system, and for this system, as you see, we see more elliptical disk structure with shorter wavelengths than we see in the near-infrared. And together with the fact that the disk is quite consistently bright in all wavelengths, and the dust opacity decreasing with wavelengths, we think that it can point us towards the potential presence of the warp. And we know that for protoplanetary disks, the warp is quite common thing to have in the disk. So this is one of the potential interpretation of this behavior for this disk. However, it is not the case for all of the disks. And for example, this is another system where the inclination that we have from the imaging and the images per se are quite consistent across the wavelengths. So as Devika mentioned, we have quite a lot of observational results. We have multi-wavelengths and multi-technique data, but what we're missing is a consistent physical model which can incorporate all of them. So this is ongoing work that I'm doing right now. So I am using the spectral energy distribution informatic visibilities from VLT, Pioneer, Gravity, and Matisse, and polarimetric direct imaging together with radiative transfer modeling code MCFOST and Bayesian optimization to come up with consistent physical disk model that can explain all of the observations and provide us the realistic constraints on the physical disk parameters and understanding what is happening in the disk. So this is ongoing work, but as a small peek into our results, this is one of our models that provides quite a good fitting for both SCDs, visibilities, and polarimetric imaging data. And while I'm not yet ready to talk about the constraints on the physical parameters, this is a confirmation that we can have a model that explains all of the data, and we can have a model that rules them all. So coming to the conclusions, post-AGB binaries can bring for us important constraints on the disk binary interaction and disk evolution processes, even including potential formation of larger grains, and give us insights into planet formation. Polarimetric observations show that they have very complex morphologies. We see a wide diversities in the surface morphology for the disks. We see that they are very efficient in polarizing light, and they're quite bright with respect to their size. We see that they potentially have quite large porous aggregates in the surface. And we see signs of the warping and even variability with morphology aligned with orbital period. And as part of our ongoing work, we are combining all of our multi-wavelength observations into the modeling to understand the underlying physics. So I think hopefully for the next meeting why galaxies care about AGB stars, we will be able to give more physical constraints and understand much better what is happening there. Thank you.
Thank you very much also for keeping by the second almost to the 12 minutes. Questions? Are there questions online? Yeah. Sorry.
Hi, thanks for the nice talk. So the systems that you showed, are they all systems that have dust standing all the way in, or I didn't really get it,
Yeah.
but or are they these systems in which the dust might have been trapped further out?
So we have, in this sample, we have just two systems where the dust is not going all the way to the dust sublimation radius. And these are the most asymmetric ones over here. And we have a new data coming up that we are starting to work now, which has much, like 10 more systems where the disk is transition disk, so the dust is captured further away. For other systems in this sample, we know that the inner rim of the disk is a dust sublimation radius.
Can I quickly follow up? And even in these transitional ones, the scales of the inner rim where you expected dust to be are too small for you to resolve that for any system, right?
Yes, we are not resolving it because typically distance to the system is from 1 kiloparsec and larger. And with the sphere, the resolution is the best one. The sphere example is around 20, 30 meter second per pixel per resolution element. So unfortunately, we cannot really resolve the inner rim. In inner rim, from what we know from informatic data, and I believe Akka will talk more on that and Ton as well, the inner rim for the transition disk is around 10 astronomical units, so like from 7 up to 15. So it's still not enough to resolve the inner rim, unfortunately. But we see it with informatic data.
Just a quick, Hans just noted this, that hole in the center is not really, maybe.
Yeah. Sorry. So because for all of the system, it's quite small disks, so we need to correct for undot polarization. So every disk in these images, it has quite high value of undot polarization, which we are correcting in our pipeline. And this central hole, it's not the real physical inner rim of the disk, it's a reduction bias that we have because we are subtracting the central part to resolve the outer disk structure. Yeah, thank you, David.
Okay, thank you. We go to the next speaker. Thanks, Katja, again. The next talk will be by Maxime.
Hi everyone, my name is Max, and I am a postdoc working with Devika Kamath. Today I'll be talking about the results from my thesis, where I have studied photospheric chemical depletion and in post-AGB binaries and how this is connected to the disk evolution. As a quick recap, when we have a binary system and one of the stars becomes a giant, it may overfill its Roche slope, which will lead to the portion of ejected material forming a circumbinary disk. And Devika has already shown this picture. This is a typical structure of a circumbinary disk, but I have to highlight that these disks come in different shapes and sizes. And we are categorizing them in 3 subtypes. There is a full disk where radial distribution starts at dust inner rim, the sublimation rim. There are transition disks which have an additional inner gap. And there are faint disks where either the disk has dissipated or the dust has settled in the midplane. Just for your understanding, from 85 post-AGB binaries known in the galaxy, about 3/4 are full disks, and the remaining quarter is shared evenly between transition disks and faint disk targets. We don't know how the depletion actually happens in post-AGB binaries for sure, but we hypothesize that it should be similar to what is happening in protoplanetary disks. So here in this slide, I will answer Elaine's question slightly. What we suppose what we think happens is that as the original gas matter in the disk, in the player in rotation, as the disk evolves, the gas starts condensing into dust. And as you would expect, different chemical elements condense at different temperatures. The first elements to condense are usually aluminum, slow neutron capture process elements, titanium, iron, as such. And as the dust condenses, the gas and dust separate, and the dust-rich matter being trapped in the disk, while the gas-rich matter accretes on the central system. And this causes us to see not the original composition of the surface of the star, but the traces of the chemical composition of the disk. Now, in the cases where disk matter is fully diluting and dominating the stellar surface, we will see something that is called photospheric chemical depletion. And on the left-hand side, I'm showing one of the theories of planet formation being a catalyst for this process of gas-dust separation from Britton et al. 2023. But David already talked about that, so I'll just go to the next slide. So even though we don't know how it happens in our systems, there are works in our extended collaboration of trying to understand how the dilution of the disk matter in the stellar surface affects the perceived photospheric abundances. What we have on the x-axis are the condensation temperatures, which are unique for each chemical element. And on the y-axis, we have the abundance, essentially the logarithmic number density of this element in the stellar photosphere. And as we start diluting more and more matter in the ratios 2 to 1, 100 to 1, and 10,000 to 1, we can see as the more easily condensed element start dropping in the abundance until we see something which we call plateau profile. And then as you dilute more and more matter, it eventually becomes saturated. One takeaway message I want you to remember, we will talk about it later, we'll get back to it later, that we don't know what is causing this process. This process is poorly understood, but one of the possible reasons is the planet formation processes. Now let's talk about what we actually observe. We have a clear separation between volatile and refractory elements, which is around 1250 kelvins. Again, I'll show similar plots over the whole rest of the presentation. We have condensation temperature on the x-axis, the abundance on the y-axis. This time it's a relative abundance relative to the sun. Now, we can see that there are some elements which are seemingly little to no affected by depletion, and there are elements significantly affected by depletion. And even though we have a demarcation, the lab demarcation between these two types of elements, in reality, the difference between little to no affected and significantly affected elements can be at other temperatures. Now, the historical way to understand how efficient the chemical depletion is in the photospheres is by taking one of the volatile elements and one of the refractory elements and getting the abundance ratio between them. And then by using this abundance ratio, we can split the post-AGB sample, binary sample, into different types of depletion from no all the way up to the extreme depletion. And here you don't need to have a close look at all the values. I just wanted to show you with this slide that there is a great diversity of the profiles, of the depletion profiles in post-AGB binary sample. So takeaway, it's too diverse to use just zinc over titanium or any other volatile to refractory abundance ratio. Now, let's go back to this picture. It is actually a picture from my thesis where I homogeneously studied the chemical composition of 22 post-AGB and post-RGB binaries. They're so diverse that the only way to do it would be to do the manual chemical analysis, and I have implemented the non-LT corrections for a dozen of a representative set of the size of about a dozen chemical elements. And we have found out that even though a lot of the targets in this studied sample were previously categorized as either as non-depleted or plateau profiles, in reality, with updated depletion profiles and non-LT corrections, they all are saturated. We came up with a robust system to describe these depletion profiles, and these results, thank you, were published in 3 consecutive papers based on the disk subtypes. Now, let's go through the poster child. You can see that for full disks, I'll quickly show that we use Bayesian analysis to fit these profiles with 3 parameters. The first one, the horizontal part, linear part, is tracing the initial metallicity. The second part traces the efficiency or slope of depletion profile, the scale, and the turn-off temperature measures now automatically the break between these 2 regimes. So for full disks, we can see that this turn-off temperature is quite high, while for transition disks, you can already see it's much lower, meaning that much more chemical elements are affected by chemical depletion in transition disk targets. Now, in faint disks, we can see that they're very similar to full disks, but actually it's just the third of the sample. Another third looks exactly like transition disk targets. And the remaining third looks like transition disk targets, but with extremely metal-poor compositions of refractory elements. So just for your information, for the scales of what's happening here is a volatile element like sulfur has an abundance which is very close to solar value, while the elements like aluminum and titanium have abundances which are 10,000 times lower than those in the sun. And as Devika already said, we hypothesized that the majority of the faint disk sample is the evolutionary endgame for the circumbinary disks. However, there are a few targets which kind of challenge this point by being too young for that. So there is some work going in this direction. Now, the last results slide that I want to show is the correlation that we tried to find between the depletion parameters on the y-axis, initial metallicity, turn-off temperature, and depletion scale, depletion slope, and parameters of the properties of the star, like effective temperature, luminosity, and infrared excess, traced by IR to stellar luminosity ratio. You can see that it's pretty chaotic. However, there is a potential to study further. For example, the upper one of the 2 subplots, 2 panels that I have circled out here, shows the possibility to cluster full disks, transition disk targets, and faint disk targets in an automatic way. And the second, the lower subplot, lower panel, shows that if we ignore for a moment the faint disks, the higher the IR, relative IR luminosity is, the more depleted the target is. So there are some things that we have found out, very mild correlations, which are to be explored further as we extend our full disk sample. But overall, in this work, in my PhD thesis, I have developed a framework for homogeneous chemical analysis of post-AGB and post-RGB binaries. We have found out that all depletion profiles are saturated, meaning that photospheric chemistry is fully, of the star is fully replaced by the disk composition. And we defined a robust system to approach the depletion study. In post-AGB binaries, we have found links between chemical depletion and disk types. We will need to extend the sample and model a bit to understand the physical processes leading to these separations. But again, there are some mild correlations that we found. And then overall, our study is a great quantitative basis for modeling of the depletion processes happening in evolved binaries. The last slide, I would like to quickly go through the future work points, major points. Again, it would be completion and expansion of the spectroscopic survey. The more depletion profiles we have, the larger diversity of these profiles we cover, the better the consecutive modeling will be. We are also trying to get together an ALMA large program to study the chemistry of the circumbinary disks. And finally, we want to perform a physical and chemical modeling of our circumbinary disks. With that, I thank you for your attention, and I'm open to your questions.
Thank you very much, Max. Again, almost to the second, 12 minutes. Questions?
They're still behind you.
Hi, thanks. Very, very nice talk. I was wondering, you showed at some point this plot with the full disk, transitional disk, and the other one. Yeah. Do all the full disks look like that with depletion only happening for very high dust formation temperature, basically? Or do you have some of these full disks that also have depletion patterns that extend to lower temperatures?
That's actually a great question. Thank you. As I showed you in one of the previous slides, in my thesis, we only analyzed 2 full disk targets, but the words that I'm saying in relation to the full disks are generally true even if you include the literature depletion profiles of the full disk targets. Of course, the biggest part of this study is the homogeneity, meaning that we use the same radiative transfer model, the same model atmospheres, and so on, so the same line lists to ensure that the depletion profiles that we come up with are very, we can actually compare it and make sure that there are no model differences. And even though we have to be very cautious about adding the literature studies, overall it seems to be the case. As you can, I can also show this plot. I kind of went over it quickly, but if you look at this part, the turn of temperatures, you will see that the red circles are the two full disk targets that I studied in my thesis, and there are also gray dots, which are the full disk studies in the literature. Especially if you look at the turn-off versus luminosity, you kind of see that the full disks, both those analyzed by me and those from the literature, seem to be occupying the higher turn-off temperatures than transition disk targets and a portion of faint disk targets. Did it answer your question? Oh, okay, sorry. At some point I got carried away. I just like this thing so much.
It's awesome. So have you tried comparing the SED, like the detailed spectra for dust properties, to the depletion temperature that you seem to get out of these studies?
Thank you for the question. We have a few people that were working in our group on analyzing TIMI2 infrared spectra, and we are also applied for JWST to get the spectra. So what we see in the actual spectra that we have for these targets, we see the alumina, we see the silicates, and that's about it. Most of our targets are oxygen-rich, but there is also a JWST proposals that we have submitted on carbon-rich targets. Thank you. Hans, there is a question.
Sorry, yeah, Sophie.
Have you derived, are these actually non-LTE abundances? And if not, have you evaluated the impact of non-LTE corrections on the scatter and or on the turn-off temperature?
Thank you very much for your question. Actually, I also went over it. So in these plots, you can see that there are different colors. So the, how do you call them? Cyan circles are the LTE abundances. The magenta squares are the non-LTE corrected abundances. and the navy triangles are the abundances that we expect should not be affected by the non-LT effects. And we can see that the profile, well, I have a paper from 2024 on two full disk targets that shows how different are the literature profiles derived 20 years ago with LTE assumptions and current profiles that were calculated with non-LTE corrections. And the turn of temperature can jump up to a few hundred kelvins, which is very important since we are essentially probing the range from about 800 kelvins to about 1400 kelvins in total.
Okay, thanks, Max, again. Next talk is an invited talk by Carmen on ALMA insights into the nebula architecture and diversity of protoplanetary nebula. Please, Carmen.
Hello, everybody, and well, thank you very much to the organizers for inviting me to talk here. And well, I'll use this time to show some results from ALMA, observations of pre-planetary nebulae, showing that this instrument is actually a very powerful facility to characterize in very detail these objects, the complexity of these objects at different scales. And of course, this helps us to understand better their formation and evolution. And before I continue, I think I need to clarify that I will be speaking about a completely different, well, not completely different, but different objects or different category of objects that are evolving off the AGB phase from the ones that we heard before and that we will continue hearing later, right? So I think I'm the only person talking about these objects that were supposed to be the classical pre-planetary nebulae, but now probably they are not anymore. So the main difference with the previous ones is that these guys have very massive outflows, bipolar outflows that are very energetic. And there is also another difference that is related to this fact, is that in these cases, it is very difficult to access to the central, empirically or observationally to the central regions. So we don't know much about binaries, orbital parameters. We don't know much about what is going on at the nucleus of these objects, okay? So, well, I will make a brief introduction on these objects. First, based on mainly molecular line observations and millimeter wavelengths before ALMA. Then I will show some ALMA results, and I will cover two aspects, molecular line emission studies, and also millimeter wavelength recombination lines, which are actually good probes of the central cores of these objects. And then I will just talk very briefly about statistics and bias in current pre-planetary nebula studies. So we already heard that the evolution from the AGB to the planetary nebula phase is very fast, and then for that reason, we don't understand very well these objects. And when the AGB phase ends, the heavy mass loss drops significantly. The star starts heating up and progressively ionizing the circumstellar material, but also the structure and the dynamics of these envelopes change dramatically, okay? And that happens very fast. In very fast time, these objects develop very diverse morphologies, which are completely different to what we observed in the AGB phase, right? Not only the morphology changes, but these objects also develop fast winds that are not common at all in AGB stars. Of course, we don't know, for the reason I mentioned before, we don't know exactly what is going on at the core of these objects, but we believe that binaries have something to do with these morphological and dynamical changes. And we don't know either what exactly mass exchanging binary systems are working here, but presumably those will manage to launch collimated jets that will sculpt the AGB wind and accelerate the AGB wind, resulting in these beautiful multipolar shapes that we see. And most studies actually point or indicate that these process begins very early, probably just as the stars leave the AGB phase, and also happens quite quickly. So yeah, there are many, many questions that we don't know about these systems, right? And we need characterization, detailed characterization of the systems at all possible spatial scales, right? So as the dominant component of preplanetary nebulae is a cold molecular gas, and most of these objects are very compact, then millimeter wavelength interferometric observations of CO and other molecules, it's a powerful tool to try and understand the systems. So based on these kind of observations, we know that most preplanetary nebulae, this kind of preplanetary nebulae, have two main components. They have fast bipolar outflows that are typically aligned along the optical lobes that you can see in for example, in HST images, like those shown here. And then there is also a slow component that is, in many cases, concentrated in the central regions and forming large expanding equatorial tori. We believe that the material that is in the fast lobes is actually the material that was already ejected in the previous AGB phase that had been shaped and accelerated by underlying jets. And the slow component will be the component that has not been so dramatically affected by this interaction. So the fast outflows in preplanetary nebulae have two main important properties. One of them is that they are expanding radially with a constant velocity gradient that indicates well, that this, or we interpret this as free expansion after a very brief and kind of violent acceleration. And also the other property is that they have a very high linear momentum in these outflows that is actually much larger than the momentum that you could get just if the acceleration mechanism is radiation pressure, okay? So that's why we call this kind of preplanetary nebulae high momentum preplanetary nebulae, okay? So we need another mass loss mechanism, and of course, we believe this mechanism probably involves accretion and binary interactions. And in this context, we would expect also to detect or to find rotating disks at the cores of these guys. But this is very difficult. And as I show you in a minute, we only managed to detect this in one of these high momentum preplanetary nebulae. However, as we just saw in the other category of post-AGB objects, which are the binary post-AGB objects that we just heard about, there are rotating disks, and the main difference with the previous ones, as I said before, is that these ones don't have massive outflows, right? And they don't have linear momentum excess. So I will not discuss more these objects because we're going to be hearing more. So I will go back again to the high momentum preplanetary nebulae. And I will, well, use this object as an example of how, again, how ALMA is a great instrument to actually disentangle the complex morphologies of these objects and also the dynamics and the kinematics, which is actually key to understand how these are shaped. So this object has a, well, it is a massive fast bipolar outflow that is emerging from a binary system that is not directly characterized, but we know there is an AGB star there and probably a main sequence companion. And what we learned from earlier studies of the molecular emission in this object is that this bipolar outflow was probably accelerated about 800 years ago, and during a process that lasted only probably 100 years or so. It was quite fast. So we mapped this object with ALMA, and we tried to cover different spatial scales from the whole envelope down to regions closer to 300 AU or so into the core. On the large scale, we found a very detailed, or we managed to get a very detailed view of the different components, and the bipolar outflow is just not anymore just the bipolar outflow, okay? We found many different components, and we found new features that are actually changing our view of how this object was shaped or is being shaped. So this position velocity diagram is, giving you some hints of the complexity and the different structures that are present here, but I will just discuss a couple of things that I consider are more important. The first one is about the central expanding equatorial ring or torus. Based on the previous data, we thought this dense equatorial structure was expanding at constant velocity, and that was ejected much earlier than the large-scale bipolar outflow. But that was mainly because we lack angular resolution. With ALMA, we are able to see a complex velocity gradient also inside of this component that is indicating that it was also formed at the same time as the large-scale outflow. So probably this is telling us that there was a kind of violent mass ejection event at the same time, resulting in these two features. The other important result from this work is the discovery, well, first of the position of the AGB star, which was found enshrouded in a cocoon or a dust and gas shell that is expanding at low velocity, and that is, by the way, not centered where one would expect. It is offset towards the south of the equatorial waist of the large-scale nebula. The other interesting discovery is that there is a second bipolar outflow that is emerging from this position, and that is oriented similarly to the large-scale outflow, but it is much slower, and also it is quite symmetric, and it's younger, okay? This one is about 100 years old. So we wanted to look at the core in more detail to see if we find more information about what is shaping this object. And then we obtained higher angular resolution maps focusing on the central regions. And what we found here is actually, we were able to resolve spatially actually the compact core. And we found a disk that is perpendicular to the large-scale nebula. And also we found also that again, we were able to locate very precisely the position of the AGB star that is surrounded also by a hot dust cocoon. And the centroid of the disk and the position of the mirror are displaced. So using this, we could get the first constraint of the orbital separation of the system, which seems to be about 20 AUs. Okay. We looked at lines, of course, and we found some species were particularly well suited and were selectively tracing this disk. And we found that the dust disk that I mentioned before was literally coated with salt, as you can see here. And if you look at the velocity map, you can notice that there is a velocity gradient that is running across, in the equatorial direction, that is a sign of rotation. So this is the first time that we detect a kind of rotating disk in a high momentum preplanetary nebulae quite robustly. So we modeled, of course, the disk, and we got actually a very detailed picture of the physical properties, the kinematics, and everything. And I would love to hear and talk more about this quantitative picture of this region with the models, people that model this kind of structures, to see if this, how this compares with their predictions. That would be actually great. And we have a similar detailed information for a few other objects. So I think we can start comparing things. In addition to the rotating torus, of course, we resolved spatially and spectrally also the outflow that was the second outflow, the young one that is emerging from the system, and we found it is expanding and is actually overlapping at its base with the salty, rotating disk, and it's also in rotation. If you look at the, well, I'm not showing this here, but we found that the base of this lobe is also rotating, which indicates a strong connection between the disk and this jet. So this is a kind of a summary of a schematic summary of the many different components that we found in this object. I didn't talk about all of them, but the main message from this is that the nebular formation and shaping history of this object is a lot more complex than we thought. It involves multiple non-spherical ejections, and also the wind mechanism, the wind collimation mechanism is still active because there is another bipolar outflow that is now being shaped. But probably the jet launching mechanism has changed because the large scale and the small scale bipolar outflows have very different properties that cannot be explained by the same mechanism. On the other hand, the rotating disks, the properties we got from our detailed study of this object are quite consistent with a Windross lobe overflow scenario to explain the torus, the dense equatorial structure that we find at the center. And also, of course, in this process, we learned that salts are actually a very powerful disk selective species in this kind of objects that we can use, of course, in other ones to try and investigate this more. So now I change to different kind of tracers, which are radio recombination lines, which are very useful to look at the deep cores of preplanetary nebulae that are starting to ionize their central regions, right? And of course, at millimeter wavelengths, the dust extinction effects are minimal, and they provide, as I will show you in a minute, a lot of information on the physical conditions and the kinematics in these central regions in high momentum preplanetary nebulae. So we did a pilot search for this kind of lines with the IRAM 30-meter telescope, and after that we follow up with ALMA, the three objects for which we detected radio recombination lines, which are the three objects shown here. I will be focusing, by the way, not on the large scale, but just at the core, right? So the first object is this one, also known as the Red Square Nebula. It is an infrared B-type star that it was suspected to be a post-AGB or evolved star because it is very similar to the red rectangle, which is, by the way, a prototype of the post-AGB binaries that we heard before. And in this case, there is an equatorial dusty torus and also some jets that are running perpendicular to the disk. And what we learn from the compact ionized region at the center is that there is also, we found a disk in probably Keplerian rotation, and also a fast wind that is being ejected perpendicular to the disk. Here I'm showing the continuum map where you can see the X-shaped morphology and also the model that we made to explain the observations. And if you look at the H30 and well, actually we have another recombination line, both show the same thing. You can see that there is a signature of a rotating disk, and also the bipolar outflow, the wings are showing signs of rotation, right? You can see the red and blue shifted emission of both components is shifted, right? So we model again this object, and that was very interesting, not only to characterize the central, the properties of the winds in these small scales, but also to constrain the nature of the central object, which turned out to be a more massive object, probably a post-main sequence star that has just left the main sequence, right? And also, of course, to get some ideas of how the fast wind is being launched. This is the second object that we studied in detail using these radio combination lines. In this one, we believe there is a binary, but it's just we believe, only based on indirect indications. And what we see with ALMA, this is the free continuum emission. As you see, it is elongated along the main axis of the nebula, but it also shows a C-shaped curvature that actually fits quite nicely with an original model that was proposed for this object by Libyan Soccer, where they proposed there was a jet that was launched by a companion that was being deflected away from the donor, from the mass-losing star, because there was this wind interaction. And by looking at the kinematics, at the lines, we get information on the kinematics. We see that the jet, in the velocity maps, you can see the clear velocity gradient along the axis, which is pointing to expansion. And it is also pointing to very short kinematical ages, as short as only a few years, right? And also, if you notice, the contours in the velocity map are not horizontal, but are tilted. And this is indication of rotation as well in this wind, right? That there is a gradient also in the perpendicular direction to the jet. And by looking at the position velocity diagram, we get more details on the details of the kinematics of the velocity field. And what this shape pattern is telling us is that there is an abrupt increase of the velocities in just two very localized positions along the jet. So this is a summary of our model. Again, we have a very detailed description of the wind, which is represented there. And as you can see, there is a non-uniform density in the outflow that probably is supporting these shocked, compressed regions there, no? As a result of the interaction of these two winds. And also we confirmed the sharp velocity race across what we call the high velocity spots. So with this, we have been able to actually provide some observational tests for planetary nebula shaping that have been proposed, in particular for these objects, and not only the analytical model by Livio and Soccer, but also more sophisticated simulations. This is the third object we mapped. Is this, well, this is a summary again of this complex structure of this object, which was thought to be multipolar, but now it also has bipolar outflows in the orthogonal direction to the main nebula axis. And regarding the central ionized region, we thought, based on our single disk data, that it was an elongated region, an elongated expanding wind. And with ALMA, we confirmed this kind of elongated distribution. It is kind of consistent with the hollow cylinder with probably a dense equator. But if we look carefully at the kinematics, that the information on the kinematics that the lines are providing, we see a global expansion, again, very small kinematical edges, but also we see an intricate pattern of velocity gradients there that we cannot easily explain. And this is work in progress, but the current model actually requires the presence probably of a couple of jets that are not oriented in the same way. So, of course, in addition to all these details about what is going on at the center of these objects, the radio recombination lines have information on the post-AGB mass loss rates, right? This is a key parameter that is not empirically constrained, and it is very useful to compare what we get from observations with the mass loss rates that models, evolutionary models, use normally to predict the evolution of these objects. And what we find is that the mass loss rates for all the objects that we study so far are higher than the values adopted by the models, which will have some consequences, in particular, a faster evolution from the AGB to the planetary nebula phase. And now just a few words on statistics and bias mitigation. And it's a few words because really we are not in the position of doing statistics, because even if the number of detailed studies or detailed characterization of this object is growing with time, we still have not enough we are far from having large and unbiased samples of objects that are, well studied. These are some examples of additional works focusing on the nebular structure and the dynamics. And of course, there are other works that focus on other aspects, like, for example, finding out about the nature of the central source, the initial mass of some object, or magnetic fields. But the thing is that most of these studies, of course, focus on the most spectacular objects, right? But this might not represent the full diversity of pre-planetary nebulae. Probably they are just extreme cases. So we need to look also at boring pre-planetary nebulae. Yes, I mean, to have an idea of the real evolution of the subjects and the diversity. So this is what we are trying to do with this Forsaken Pre-Planetary Nebula project. We are focusing in this first stage in this kind of planetary nebulae that have HST images that look point-like, so no trace of nebulosity. And we are studying now in the first stage again to see if there is some circumstellar material around these objects based on observations of CO, first with single Ds and next with ALMA. So what we find is actually we find circumstellar material in all of the objects, even though HST doesn't show any interesting nebulosity. And we are also finding that about half of the sample saw high velocity winds that are indicating the presence of fast bipolar post-AGB outflows that are very compact. So they are starting to develop inside of a much larger AGB wind. So this configuration suggests that these objects could be younger than most well-studied pre-planetary nebulae. So in this sense, this object could be actually key to understand planetary nebula shaping in its origins. Another emerging trend is that these forsaken pre-planetary nebulae seem to be less massive and probably have lower mass loss rates than the well-known pre-planetary nebulae. But well, we still need to complete this study to be able to understand what kind of objects we are dealing with here, and also together with more ALMA observations of the well-known pre-planetary nebulae, eventually, I guess, we will understand the full diversity of pre-planetary nebulae. And these are my concluding remarks. Well, pre-planetary nebulae are key to understand AGB to planetary nebula evolution. ALMA is also key to get a detailed characterization of the large-scale morphology, but also to the deep core regions of these objects. And we need to pay attention also to novel tracers, like or less used tracers, like millimeter wavelength recombination lines or the disk selective species that I talk about. And also we need a specific predictions or compare predictions from theories and models with these detailed characterization studies of pre-planetary nebulae. And of course, we do need more data to improve our statistics. And well, thank you very much for listening.
Thank you very much for these fantastic analyses, but also to plead for boring objects. So, questions? Yep.
Hi, Carmen. Very cool objects. I have a question about OH231. You mentioned that you have the two slightly misaligned outflows, right? And one is the high velocity outflow, and then you have this low velocity outflow. And you mentioned that the collimation mechanism probably is the same, but the launching mechanism would be different. Could it be that the launching mechanism still is the same, but that the system parameters would have changed in such a short time so that you don't need to invoke a different mechanism?
We don't know. I mean, I cannot answer this, but yeah, I think it's possible. I mean, also you expect after the ejection, the violent ejections that resulted in the formation of the large-scale nebula, of course, the orbital parameters probably didn't stay the same, right? And not only that, but also you expect some recoil maybe of the system because the ejection was not symmetric. The ejection of the large scale, so, and also of course it could, if the ejection is happens in very short amount of time, of course you also have the effect of the orbital motion because this one is a 50-year long period. So it could be a combination of things. I don't think just a stable and quiet, like for example, Windrow's low overflow thing was working also at the beginning. Maybe not, or well, maybe yes, but the launching mechanism was really, really different.
More questions?
So also OH231. I think you said that the dust needed to be very hot, like 1400 Kelvin.
Yes.
And so my question is there infrared data that we can look at? Because it's oxygen rich. At 1400 Kelvin, you should be seeing crystalline features.
Yes, actually there is, well, what we thought, what we speculated with the idea that maybe is the dust that is producing, or that is mainly composing this cocoon is probably L2O3. This is alumina, no? Yes. And this has been actually suggested based on also some infrared data. Yeah. And also we thought about this species because it is one of the ones that sublimates at higher temperatures.
Okay, thank you very much again.
Thank you for your question.
It's now a coffee break, but please be back at 11:15. And thanks all the speakers.
right, we're going to start in 20 seconds. So, yes. Please settle down, everyone, so we can start on time and end on time. Okay, so a kind reminder to do the voting. It will close very soon. And for the very last session of the conference,
Devika.
oh,
It's me.
sorry.
Actually, sorry. So I interrupted you.
That's okay.
So we decided that since we have well, some students still that gave talks today, we will allow the 15. So we will shift a little bit the announcement of the prize. And so the last 15 minutes of today, which is where we were supposed to, you will have a time to vote, review again the posters, review again the abstracts, the talks. And so there will be these 15 minutes where you can do that, and then we will do the announcement. So we will close the voting at 12:30 lunchtime. Thank you.
All right. Thank you, Claudia. So the first talk for this session is we're going to continue back on the post-AGB theme, and Hans van Winkel will talk on tracing disk binary interactions through post-AGB disk wins. Take
More or
it
less.
away, Hans.
Okay,
More or less.
thanks a lot. So we go back to the, let's say, optically bright post-AGB stars, and in contradiction to what Carmen was talking about, these are really optically bright. So you see the central star, and that allows us to do some monitoring. So it's a large collaboration, as you've heard before. It's, let's say, Macquarie, Leuven, and Madrid. So the common building blocks are the circumbinary disk, and you have, of course, a central binary. All the light is produced by the post-AGB star, but today, or this talk, will mainly be about the unseen companion. So the companion of the very light, so very luminous post-AGB star. So what will we use is not spatially resolved data, but time resolved data. So together with the Royal Observatory, the ULB, Tautenberg, and Geneva, we built a spectrograph, and that spectrograph allowed us to really do some systematic work on following objects which are bright enough. It's a 1.2 meter telescope. So we need so optically bright objects, and we started a long monitoring campaign, and we found the binaries. So nature was very mild to us. We started the campaign, and whatever there is a near-infrared excess, which is indicative of that disk, we find a binary. I won't talk about the orbits, while there is a lot of interesting stuff about those orbits, but it's good to mention that the typical orbits have a period of about 100 to a few thousand days, and they are mainly eccentric. So we find a lot of them. You see some of them have more scatter, and that means that they're pulsating. And so you need a lot of data, actually, to come to the orbital movement, because the pulsational variability is quite large in amplitude. So in total, we have about 40 objects with spectroscopic binaries. And in fact, it is, if you have a near-infrared excess, you have a disk, and then it's a binary. If you don't have a near-infrared excess, so you have an outflow, we don't find the binaries. So the specificity of a near-infrared excess really helps us to select the binaries. They're not embedded, so whatever the embedded sources, of course, we cannot tell about the link between the embedded sources and the sources.
Sorry, can you get your microphone closer, please?
Yes.
For the online people.
Okay. So what can we do with the spectra? More than just the orbit. So here I show you, you take a spectral line, you put it in velocity space, and then you put the orbital phase in the y-axis. And just for clarity, we have two orbital phases. So we show the data twice, but it's a strong, let's say, visualization of what is happening. And so in the left, you see a nicely, clearly Keplerian orbit. On the right, you see an emission line, which is tracing gas, which is linked to the center of mass and not to one of the components. And now we have a movie. Yes. So what happens now if you turn to H alpha? In H alpha, you see at some point, and it's always when the companion is in front, you see the appearance of a strong, thank you. You see the appearance of a strong absorption component in the blue. So whenever the companion, which has not a lot of light, so entering the line of sight, you will have a blue absorption component, which has a velocity up to, let's say, 500 kilometers per second. And okay, the next slide, please. Yes, we see that a lot. In fact, almost all objects show the same. Take care, the zero phase is here random, but it's all, so you have to believe me, that it's always when a companion is in front of the main star, you see that absorption component happening. So sometimes it's very blue, like here. Sometimes you will always see it. There's always an absorption component, and I'll come back to that later when we do the modeling. So what can we do? So we see it a lot. So we have a lot of objects that really, thanks to the monitoring for a decade or more than a decade, in fact, we have enough of data to really trace the outflow of the companion, is originating in the companion. Because, so what we do, we model this outflow. So this is the positive B star. We have the unseen component, which has probably an accretion disk. If we take a cone with a velocity, angle velocity, and so an angle-dependent velocity and an angle-dependent density, you can model, because you scan, in fact, the jet at the region where it is accelerating. So the parameters that you use is jet opening angle, tilt angle, angular velocity structure, density structure. And of course, since we have the binary orbit, we can see which of the line of sights, so the traces, let's say, go through the cone or do not go through the cone. And it works quite well. You see here, on the left, here's the data. On the right, you see the model. And on the right-hand side, you see how this is reflected in the parameter space, that you have the orbit, you have the main star, which is given all the luminosity, but light going through the cone is deflected because of scattering. And the light, so the atom that it finds has a certain velocity, an outflow velocity, and that's why it's blue shifted. So you can do it. And if you look polon, or almost polon, in any line of sight, you will go through the cone. And that's why on some objects, you see that absorption component all the time. So this is the become. So you see, first of all, what do you learn from that is, first of all, there is not yet physics involved, but we can conclude already that the opening angles are wide. The velocity is quite fast, but it relates to the escape velocity of a main sequence star and never a white dwarf. You have high density, low velocity in the cone, and low velocity and high density at the edge of the cone. So in the center, it's high velocity. At the edge of the cone, it's low velocity. Then we go to young star objects, and this is another example in which young stellar objects can inspire us to see what we see. And if you look at jet launching mechanisms for young stars, and we use the models, the MHD models of the group in Grenoble, then you can in fact use, okay, 5 minutes, you can use their models to see what kind of characteristic outflows they would give around our companion. Of course, we don't trace the central star. We trace only a line of sight through the jet. So we have to put our central object outside the disk of the companion disk. We don't know the central star. We only know the mass. We don't know, of course, the magnetic field, but it seems to be a very efficient way to include those, let's say, disk winds with high velocity. And it's a natural way also to explain the wide opening angle of those jets. So you can do that, and in fact, it gives you a natural, let's say, quite well constrained velocity gradient between the central part and the outskirts, and the associated density profile. So that works quite well. So the cold disk wind models provide the needed opening angle. It provides the needed density structure. But of course, there are some interesting problems associated with it. So this is an example in which you see on the left-hand side the data. In the middle side, you see the background spectrum that we use of the light that goes through the cone. And on the right-hand side, you see the model. And you see we cover a quite large range in orbital phase, and that works well. So that means the opening angle is quite wide. But we do need a lot of accreted mass. So this is mass accreted from the circumbinary disk, because the main sequence, the post-AGB star does not provide enough mass loss. So we need to accrete mass from the circumbinary disk to the companion. Max told us about accreted material on the main star, but we have accreted material on the companion. But it's a lot. So it's really a lot. And why is that a lot? First of all, it's because it's always in absorption. We never see it in emission. And that absorption means that there must be hydrogen atoms in the first excited state because it's in H alpha. We have H alpha, we have H beta. The same profile appears in H beta, be it in a lesser extent. But that gives us, given that the background star is sometimes only 4,000 Kelvin, you have to have a jet which is cooler. And that means that not a lot of hydrogen in the first excited state. So we need quite a lot of mass in order to explain those. And it's uncomfortably high. So we have to find a way to reduce that. Another interesting thing is, if you look at the models, an accretion disk, of course, rotate, and that means also the jet should rotate. But that rotation is never seen. We never see on the right-hand side an absorption component appearing, because that would be the light that is going away from us. It's always coming towards us. There is never an absorption component in the right-hand side, while you would expect it in a rotating structure. But we never observe it. So this is also, in fact, we have to find a way to suppress that rotation. So, science question. So we do make progress. We understand the jet creation, and we observe the jet creation process in a lot of systems. We still have to make the correlation between the SEDs, because the SED gives us how much material is in the circumbinary disk, but it's accreting to the companion, and that accretion process is very efficient because we see those jets in almost all systems. But we have also quite a lot of questions associated with that. So the disk creation, of course, but now we have, it's a complicated system. It's become more and more complicated because we have the circumbinary disk and we have the circumcompanion disk. And the circumcompanion disk is where the jet is created, which is understandable, but still we need a lot of accreted mass. And so I'll leave you with all the questions. And so I think the next several of those workshops will be needed to resolve all of those questions, I'm afraid. Which is also important, I think, for the next generation of instruments, is to really understand the interaction between the different components, because that is really driving the evolution of those systems. The link to the more embedded systems is something that is also very interesting. And for that, we have to understand why those do not have, so they're optically bright. They cover a mass range in between, let's say, up to 3 solar masses, in fact, the companions. They go up to 3 solar masses. So the mass range is not very different than the very embedded sources. So there is still a lot of work to do in understanding let's say, this group is now quite well identified, I would think. But there is still a lot of work to do in order to understand the connection between those objects and AGB progeny, but also or precursors and PNE progeny. Thank you.
Thanks, Hans, also for sticking to time. We have a few minutes for questions. Yes, I was looking straight at you. Please go ahead.
Okay. Thanks, Hans. Very nice talk, as always. I was wondering, 2 things. Are the accretion rates of the companion constrained in any other way that you can compare to the masses you need in the...
So The only way so this is an indirect way, of course, because we are sensitive to the amount of material which is in the first excited state. But we have thermal emission of those disks also, and Toon will talk about it in interferometry. You can resolve, and some objects, and Akko probably also, in some objects we resolve the circumbinary companion disk. And it's about, in H, it's about 8% of the light. But we did not translate it yet to, I mean, for the moment, it's difficult to measure the temperature because it's just in the Pioneer wavelength domain, and it's a little bit small in wavelength coverage in order to estimate the black body temperature of the disk that is needed to translate it to mass.
And when you convert the absorption to a mass, how do you calculate the excitation of hydrogen? Is just thermal excitation now, or do you have a radiation field?
No, it's thermal excitation. Yeah. And then, so we use, in fact, because we have the same in H beta and H gamma, so we use the Balmer decrement to estimate the gas temperature.
And just to add, Hans, you also have the accretion rates through the depletion as well, because you can.
But that's also very indirect.
But there is another estimate if you,
But so in order to understand the depletion to that level that we see it, you can model that. You can use a model to see. So the star is now 6,000 Kelvin. If you accrete it with a certain number, then, and you evolve it to the HR place or the HR diagram that is located now, you can have an estimate on what is needed as an accretion rate in order to link both the abundances and the position on the HR diagram to time. And also there, we need a quite high accretion rate.
So I'm going to get Lane's very quick question. And
it's very quick, and it's linked to that. Well, Mats is also calculating the accretion rate on the companion, so not on the star. But if you say quite high, can you quantify that?
Well, high means that so the mass of the circumbinary disk is only 10 to the minus 2.
Yeah.
That means if you accrete at 10 to the minus 4, you can only live 100 years from that accretion alone.
Yeah.
Because you see the abundance, you see in the CO maps, you see that the gas is also expanding in the radial direction. So there is also mass loss on a, let's say, a normal disk will evolve pushing the gas outside. So this is only the gas which is accreted onto the companion. Yeah. And that makes it challenging. First, we see them everywhere. Mm-hmm. So all our objects have those disks and have those H-alpha profiles. But if it's such a short mechanism, so if it's lasting only 100 years, then we have a time problem because we see it everywhere and it should be temporary. And that is a conflict.
Yeah. So we should take that discussion out of this session. But thanks again. Thanks to Hans, and we'll welcome Akka. So the next talk is by Akka, who's going to talk to us about spatially resolving the inner regions of the disks around post-AGB binaries. Take it away, Akka.
Thank you. So I'm Akka Corporal. I'm a research fellow at ESO here in Chile. And today I will talk about the AGB binary progeny. So again, staying on these post-AGB binary systems. And I hope to convey to you today how we can study these kind of systems to progress on both stellar evolution and disk physics. So Hans just talked about the binary system and the jets. And in this talk, I want to focus again on the circumbinary disk. And more specifically, in this talk and also in the next one, we will focus on the very inner regions of these disks by spatially resolving them using infrared interferometry. And that's the typical distances of these objects, which is about 1 kiloparsec or so. And with current facilities, we can reach now milliarc seconds scales, which corresponds to 1 astronomical unit or so. with such skills, we can progress on both stellar evolution and disk physics by answering a couple of questions or try to address a couple of questions, and especially related to stellar evolution. We want to understand how the circumbinary disk influences the stellar properties, or how the further evolution of the stars in general. Because this reaccretion of the material of the circumbinary disk onto the central stars will influence the stellar properties, and thus the further evolution. And this is important for our binary evolution models between the AGB and the planetary nebula and even beyond. From the disk physics perspective, we want to understand what kind of physics is at play to grow the dust at the sizes that we see, but also related to the timescales, because these disks are way shorter lived than other kind of disks like protoplanetary disks. And I think we can get significant constraints on the initial stages of planet formation, not only for maybe planet formation possibilities post-mid sequence or the second generation planet formation that Devika was talking about, but also for the ones in the younger stages. So to answer, well, actually what I wanted to say here, sorry, now I'm going in the wrong direction. What I wanted to say here as well is that by doing these kind of disk physics studies, I want to address the big open questions in planet formation theories today, namely the timing, location, and mechanisms of planet formation. And I think the only way in doing that, or maybe not the only one, but one of the most efficient ways is doing this in different environments. And these post-AGB binaries are, we can actually do this with these post-AGB binary systems, as they have different lifetimes, different properties as well, in addition to all the properties that are in common with with protoplanetary disks. So in order to address these kind of questions, I want to remind you of the different disk structures that we have. And this is based on a catalog of the post-AGB binary systems in our own galaxy, which are 85 actually. And these are mostly in the near and mid-infrared. So if the disk has a very well, if the excess of these, the infrared excess starts at near-infrared wavelengths, we call these systems full disks. And if the systems lack a near-infrared excess but have a very strong mid-infrared excess, then this indicates that there's a cavity in the inner disk distributions, which points to the inner rim being farther away from the sublimation radius. And we call these systems transition disks, like in the protoplanetary disk research. And then you have another kind of in-between state that we didn't talk about yet, but these systems have a lack of near-infrared excess with a very mild mid-infrared excess. And just based on the SED, it's impossible to distinguish whether these are full disk or transition disks, so we need to spatially resolve the emission to quantify this exactly. So these kind of systems only have a common wavelength regime in where they emit, which is the mid-infrared, so we can probe them with the Matisse instrument on the VLTI. And we did this for 11 post-AGB binary systems so far. 5 of these systems have a near-infrared excess that starts at, have a near-infrared excess, also a mid-infrared excess, of course. And 6 of the systems have a lack of near-infrared excess. But these 6 systems also have a strong depletion pattern. And we targeted those with Matisse. We tried to do the modeling, and here are the results. So here I plot the inner rim radius as a function of the sublimation radius for the 11 post-AGB binary systems that we probed. And this gray shaded area indicates the one-to-one line where the dust is expected to sublimate. So these are temperatures of 1,000 to 1,500 Kelvin. And what we find is that for the full disks, or for the full disk candidates in general, so the ones that have a very strong excess starting at near-infrared wavelengths, we find that the inner rim radius is located at the sublimation radius. And for the other 6 systems that have a lack of this near-infrared excess, we find that the inner rim radius is several times the sublimation radius, with absolute or more physical scales of 3 to 25 astronomical units. So this means that there are some transition disks around these evolved binary systems as well. So what is the origin of these transition disks? Well, photoevaporation is actually quite unlikely process for at least part of the systems, because we don't see any high energy photons in these systems. So, but there exist actually other possibilities, like we have this binary, so dynamical truncation of the binary would be one example. And this is, we try to do this for one system. I must say this is also one of the larger binary interaction systems, or at least one of the larger, longer periods, but also one with the largest physical cavities. And we find that this is, that the orbit, we could find the orbit with infrared interferometry, and it's very unlikely this cannot create such a large cavity. And other possibilities still exist, namely the presence of a substellar companion or enhanced grain growth. But at this point, we cannot do more than just speculate. Then there's another infrared interferometric observing campaign that we did, which is the Inspiring Large program, which ran between 2019 and 2023. We targeted 10 post-AGB binary systems with the near-infrared VLTI instrument, PNEA, and gravity. And they have a range of binary and stellar properties, as well as disk properties. The sample consists of 9 full disks and 1 transition disk. And the main goals were to do image reconstruction of the very close circumstellar environment, try to understand the physics, and this is where Toon will be talking about in the next talk, and try to quantify and trace the disk binary interaction, which can be done with the gravity instrument because of its high spectral resolution mode as well. So we can, in the K-band, gravity operates in the K-band, and in the K-band we also have the accretion traces, bracket gamma and CO. And from there we can try to see if this is present or not. And here I show some of the results. So this is the continuum emission at 2.2 micron overlaid with some bracket gamma and CO. Oh, sorry. Spoiler. Overlaid with some bracket gamma and bracket gamma emission as well here, and CO emission. And it's very nice to see that all these emissions come in the very inner regions of this disk. It's not coming from the, we cannot find any signature of the circumcompanion accretion disk, but we do see some emission in these very inner regions, which is not for every object, but for these and a couple of more objects, it's very cool. And also I wanted to highlight this object, because we find that for this object, we have a very complex structure. So this object has a jet, it has a circumprimary disk, and likely also a binary disk, which we hope to be traced with VLTI Matisse in the next months. So I also wanted to give a little bit of future prospects in the next decades. What can we expect with the ELT and beyond? So with in a synergy between the ELT and VLTI, I think we can also probe we can try to answer some of the questions that we have, both in stellar evolution and in disk physics. In terms of stellar evolution, I think we can try to understand the effects of the disk across metallicity, because I think with METIS at very high angular spatial resolution combined with VLTI, we can go fainter to fainter objects. We cannot resolve the disk with METIS yet or VLTI yet, but I think we can go in this direction. And also related to the disk physics, I think we have a nice synergy in terms of chemistry, especially related to the PAH emission that we see in some objects, and the nanodiamonds as well. And then going even beyond, what about the 2040s? So we cannot resolve this object yet. So one thing is actually that we need higher angular resolution to try to answer some questions related to the accretion processes, and the universality of disk physics across the ASR diagram. And this brings me to my conclusions. I hope I somehow conveyed that the disk around post-AGB binary systems are ideal lenses in the fields of stellar astrophysics and disk research as well. And that high angular resolution observing campaigns can help us really to uncover the various scales, but also especially the inner disk regions where the sublimation is happening, where disk grain growth is happening. And I think also that there's many avenues of progression on the horizon. Thank you.
Thank you, Akka, for that very interesting talk. Do we have any questions for Akka? Yes. Give me a second.
Thank you. Very nice talk indeed. I have a question for the, you said that you're using the lines of that are measured with gravity as well. Is the resolution, the spectral resolution, high enough that you can actually see the velocity field inside the disk? Or can you disentangle the circumbinary disk from a closer disk maybe by velocities as well? Is that a possibility?
I don't think so. I don't think the resolution is high enough. I also don't know how to see it actually, but because it doesn't seem that the lines are located really in the circumbinary disk itself. It seems to be really inwards of the circumbinary disk.
Yeah, okay. I think for a system like U1 or so, which are not really face on, but more inclined,
yes,
that might be possible, no? To see where the velocity changes, but I don't know if the resolution is good enough. Yeah.
I think we also need multiple scales here, and for this one we only have one scale, so we only have the medium baselines. So
okay,
probing, yeah, I think we need even the longer baselines, to be honest.
Okay, thanks.
All right, thank you. We have another question also here.
Beth Sargent, SETI Institute. You had mentioned grain growth in the disks. In protoplanetary disks, the models that include grain growth have the disks flattening, like the angle of the opening angle of the disk is narrower when they experience grain growth. Is there any evidence for that in post-AGB disks?
You mean at the inner disk rim or further away?
Just globally with the whole disk.
So we do have the grain disk settling in the midplane, but we have one ALMA image on an edge on ALMA image. So this is like one kind of thing. Right. But in our models, when we try to reproduce all the observations, yes, we do see strong indications of disk grain growth. The disk settling is actually quite strong according to the radiative transfer models.
Thank you.
Thank you, Akka. Thanks, Beth. Any last questions? I can take a quick question if anyone has any. Okay, if not, then thank you, Akka, and we will invite Tone. So the next talk is by Tone. He will be also talking about the inner rims, but will be using Pioneer.
Should be now. All right. Good day, everybody. I'm Tone de Prins, joint PhD student at Macquarie University NKU Leuven, and I have the honor of being the last student speaker of the conference, actually. I wanted to be talking today about a substructure hunt in post-AGB circumbinary disks. Would you believe it? So I hope you're not tired of them. And this is work I performed in collaboration with Akka and Hans and Devika. So jumping straight into it, I've again shown a nice SED for a disk-bearing binary post-AGB, and you can see the stellar photosphere, and also an extended near-infrared excess emission. But I wanted to stress that about 30% of all optically bright post-AGBs show this kind of disk excess. So these are not a fringe phenomenon. They're a very, very common product of stellar evolution. And like Devika mentioned, we have trouble forming them in simulations, but it seems nature doesn't care much about numerical stability and such. They're highly similar to protoplanetary disks, which of course begs the question, well, is there also substructure formation in that case? Because I assume you all have seen plenty of ALMA images where you have very structured protoplanetary disks. And might any of these substructures be indicative or conducive to planet formation processes? We look at the outer rim in ALMA, the outer disk in ALMA at the midplane, and in sphere in the upper layers in scattered light. But to really resolve the inner disk, you need optical interferometry because this is several AU size at kiloparsec distances. So the big picture, we have the dusty circumbinary disk, outer layers in sphere, as you saw in Katja's talk. We have accretion onto the bright post-AGB primary, as you saw in Max's talk, with the refractory depletion. So accretion streams free of dust falling back onto the central star, and even a circumprimary disk in the case of Akke's UMON model. The same thing onto the secondary star, and in the general disk cavity, again, bracket gamma emission in Akke's Iris-08 model, and of course the jets that you saw in Hans's talk. But the big question here is actually, well, what about the morphology of the inner circumbinary disk itself? If there is so much intercomponent interaction from the big circumbinary disk onto the central stars, well, what about the inverse? Does the central binary affect the disk structure and morphology? So this was part of the aims of the Inspiring Large program by Jacques Luska with VLTI Pioneer specifically. And I will be showing you the results for 7 galactic full disks, really showing you images to constrain the detailed morphology of the inner disk rim using non-parametric image reconstruction. The goal here is to really reveal structures and to look if they might be indicative of intercomponent interaction, either with the central stars or possible embedded substellar companions, and also to see if there is any kind of substructure that might be conducive or indicative of planet formation processes. For this, we use the combination of the organic algorithm with the Sparko approach. So organic is our neural network image reconstruction code, and all it does is really take in radiative transfer models and encode those as a sort of astrophysically inspired prior on your image reconstruction process. So it gives you sort of a probability of diskiness, let's say, a proxy for that, and that's what you combine with your data likelihood from your Pioneer observations to really get your final image reconstruction. We combine that with the Sparko approach, stands for semi-parametric approach to the reconstruction of chromatic objects, so quite a mouthful. But all it means really is that you model your central stars parametrically, you give them a spectral index and some simple parametric geometrical shape like a uniform disk or a point source. And what that allows you to do is really just reconstruct the flux from the circumstellar environment in a chromatic way. So you reduce your dynamic range for your imaging and you can use all your wavelength channels simultaneously, which greatly helps with the image fidelity. So diving into the results, let's start off with a boring case, or maybe if I put it more diplomatically, the canonical case. And sort of to vindicate this system, I've also shown Katja's sphere image again, because this system, Iris 15, has a nice secondary ring in the sphere scattered light. But if we zoom in onto the Pioneer scales, you can see this thermal emission from the inner rim, which is nicely concentrated along this ellipsoid, perfectly asymmetrically, pretty much. And this is exactly what you would expect for a smooth, structureless disk rim that you're looking at under an inclination angle. The reason why one side is brighter than the other is because the darker side is actually the near side compared to the observer along the line of sight, which blocks its own radiation because these disks aren't thin, they're very thick and sort of flared, bowl-shaped. So there is some self-absorption going on. And you can see that in the radiative transfer model as well. So this is 1 out of 7 systems. As you might guess, this means that none of the other ones are actually smooth and structureless. One effect that we see pop up very commonly is actually that as the primary star is orbiting, and you can see I've denoted it by a gold star here, and also the secondary, the secondary star, in case we see the thermal emission from its secondary disk. You can see that as the primary approaches the disk rim, it actually preferably illuminates one side, and you can actually see this in the emission itself. So we don't know exactly what's going on here. Is this just an increase in local temperature? Is this an increase in scale height, a change in the disk shape? We don't really know. It might be a combination of all these different factors. But one thing is clear, it's that the motion of the primary in the binary orbit is heavily affecting the structure and the morphology of these rims. So obviously, when we start modeling these disks in the future, you can't just assume the primary is nicely in the middle, illuminating everything symmetrically. Obviously, this needs to be taken into account. Next, maybe my favorite system, IWCAR. Again, showing the sphere image on the left, you can see this dark band, which is actually the midplane of the disk. And then as you zoom in to IWCAR, you can see there's a whole bunch of stuff going on. So we again have our central stars. There seems to be these flux arcs very close to the central stars themselves. But then to the west, suddenly, you also have this huge arc in thermal emission. So we're not really sure which one of these arcs in the Pioneer image is the actual inner disk rim, or whether there's more complex structure going on. So it could be that these inner arcs are just accretion streamers, so maybe shielded dust or more refractory dust falling onto the central stars, and then the structure to the west is actually the actual inner rim. We don't know if this represents a warped or a torn ring, like Katja mentioned during her talk. And you can actually see a nice simulation on the right from Krause et al. 2020, where you can see a disk tear forming. And we don't know if this might even be a spiral in the disk or a feature in an outflow. For example, for HD 101 584 from Kluska et al. 2020, we actually had a secondary ring, which was some condensation front in a disk wind outflow. So it's really unclear. All we know is that it's really complex, and we have to figure it out further. Also, some other substructures. So for HD 108, 015, and HR 4049, if we compare it to previous observations, it seems that the brightness enhancements along these rims are not actually following the primary star. So they're moving at their own independent rate, slower than the central binary. And this might be either substructures that are formed dynamically, induced by the binary torque, or they might actually represent vortices, Rossby wave instabilities. Now, there's very different conditions for these two formation mechanisms. For binary-induced substructures, your orbit needs to be large enough. For Rossby wave instabilities, you need some initial pressure bump in your gas pressure profile of the disk, which means either it's planet-induced, like Devika mentioned, or an alternative is actually magnetic dead zones. What I mean by dead zones is if the gas in your inner disk is magnetically coupled, so it's ionized enough, and accretion is actually mediated by magnetic turbulence, then if you have a steep temperature drop at the sublimation front, what happens is that the gas inwards of that is ionized, turbulent. Outside, it isn't turbulent anymore, and that's what we call a dead zone. And at the edge of that transition, you get a heap up of material, a pressure bump, and that can become unstable and form this kind of vortices as well. So you have all these nice simulations for these cases, but there's a lot of significant unknowns when it comes to inducing these in post-AGB disks. For the binary scenario, we need to know the orbital parameters, but we don't know them to an extent certain enough to be able to exclude this scenario. For Rossby wave vortices, you need to know about the viscosity, possible planets, and even the ionization state of the inner disk gas, which we're really not that sure of at this point. So, in conclusion, these inner rims are heavily structured. Out of the 7 systems we've imaged, only one of them actually shows the canonical case of a nice, smooth, symmetric disks. All of the other ones are fully structured. There's a clear reaction, thermal reaction to the primary, which we need to further investigate with radiative transfer and hydro modeling, preferably even coupled modeling. But the nature of the other substructures is really unclear. So are these warps, spirals, in the case of IWCAR? Might they be Rossby wave vortices, or might they be binary induced somehow? Now, in terms of open questions, to tackle the origin of these substructures, what you can do is imaging time series, because most of these mechanisms have very different time scales in terms of angular movement. So do they rotate at the local Keplerian velocity? Do they follow the central binary? If you had a nice imaging time series, we might be able to discern and exclude many of these scenarios. Also, we want to look at the processing and the mineralogy of the dust, VLTI Matisse would be great for this, especially in N-band, because then we can look at the silicate feature. And we can look at processes like crystallization and really say whether crystallization occurs preferably in these substructures or whether it's spread throughout the whole disk. Also, the link to the other physical processes like dust depletion, which we trace with the depletion processes in the photosphere, like in Max's talk. We're not really sure because these processes pop up constantly. We always have dust depletion, but we don't know how it relates to possible substructures in the disk, which might be the dust trapping. And on the other hand, we have, of course, planet formation, because vortices like these and other substructures can really, really concentrate your dust and maybe enable the physical conditions for further instabilities, which might lead to planetesimal formation. So we're planning to publish this, submit this work actually to ANA in a few weeks. So if you're interested in this, keep an eye out, because it should pop up on the archive in a couple of months, depending on how happy the referee is, of course. Thank you.
Thank you, Tom. That was very clear and interesting. Everybody loves Fourier space. Any questions? Yes, Claudia, please.
Ton, well, first, a very nice talk. Thank you. I found very interesting. Can you go back to the previous slide, the one with the summary? So indeed, you are not excluding that some of these structures that you see are maybe kind of, they are connected to spirals, because one of the things I was asking myself is that like on the AGB, we don't really see a lot of disks, we see a lot of spirals. On the post-AGB, you see a lot of disks and you don't see the spirals. So is it possible then indeed that what you are calling disks on the top are what is coming out of the Roche lobe and the spirals that we see in the AGB, and what you have after are the disks that we see, don't know where they are?
I don't know. I wouldn't exclude that maybe as a possibility. But in that case, I would be surprised that the signal is so strong, because I would think that if it is just, well, let's say an exclusion of matter still from the primary star, that it would be weaker. This is really, really a large concentration of matter in relatively small space. So I don't know if any of let's say, the Roche lobe material that the star can still give off would cause a signal this strong.
Well, it's Roche lobe. Well, the people that know Roche lobe overflow will know much more, can tell you much more than me. But I mean, there are still a lot of years between one stage and the other, right? And we have in the middle what Carmen was showing. So there can be other physical mechanism happening that produce that. I'm just intrigued by the shape and this mismatch that we have at this stage between the two stages. Not?
Yeah.
Maybe food for thought.
Interesting question.
Thank you, Claudia. Any other questions? Yes, there's one from Beth, and then we'll take Theo.
Beth Sargent, SETI Institute. Are the inner radii of these disks, do you know like the dust temperature at that radius?
Inferring the temperature is really, really tough. What we typically do is just assume silicates, so somewhere from 1,000 to 1,500 Kelvin, given some leeway, given that we don't really know the vapor pressure. And it seems to be that the angular size you would expect for the sublimation radii in that case match pretty well to what we derive directly from the images. So what we can say is dust sublimation, assuming silicates, is consistent with the sizes we find, but we don't really know the temperature. What you can do is try and look at the spectral behavior and then infer a temperature, but that is really degenerate with the qualitative shape of the radial intensity profile, you assume. So that's tricky. You can make relative assessments, but making absolute assessments in temperature is tough.
The reason I was asking is there are things that like are aluminum bearing that have higher dust sublimation temperatures.
Thanks.
We're a bit out of time, but we'll take Theo if it's a quick question.
Yeah. So I don't know if you mentioned, sorry if you did, but looking at these plots, it looks like your well-behaved source is the only one for which the separation between the two is much smaller than the size of the structure. Is that the case, or?
No, not really. For example, I don't know which button is actually the laser pointer. This guy, the rim center is given by the white dot. The golden star is the primary, but actually there the primary motion is unresolved. The only reason you have an offset between the rim center, which in this case is the photo center, it's not the actual center of mass, and the star, which is where the actual center of mass lies, is because this emission comes from high up in high vertical layers in the disk. So it's really hard to make the connection between the current position of the star that you see in the image and the actual center of mass of the disk itself. So it's a bit deceiving.
Okay, so we're running out of time here, so we will thank Tone once again. Thank you very much, Tone. And we will welcome our final speaker for this session, Javier, who will talk to us about big grains. We like big grains, make planets. Big grains in red rectangle.
Microphone.
Yes, please, your microphone.
Okay, now? Okay.
Perfect.
So
Thank you.
thank you very much for the invitation, and it's an honor to close this session. And I'll talking about big range in the red rectangle, another post-AGB binary with rotating disk. So I hope you are not already tired of those. But I will focus a little bit on the molecules because they also have molecular emission, and nobody has addressed this issue. Well, I'm of course speaking on behalf of the whole team that is listed up there. Okay, I think I can skip the introduction of this kind of objects. We already have heard, well, the whole day, except Carmen talks were focused on this kind of objects. So I will focus on this lower part that is related to the dust molecular content. You have seen this scheme many times, but in all these schemes, there is one part that's missing, is that from the rotating disk, which is rich in molecules and dust, there is wind coming. It's not the wind coming from the companion. It's a slow wind, no momentum excess, very little mass, 10 to the -2 solar masses, that is escaping from the rotating disk, and of course is rotating a little bit. So this is another peculiarity of these objects. We have all the ingredients to launch jets, and we do launch jets, but we don't need this new mechanism to power the outflows we see that are being released from the disk. Of course, you can use interferometry to have a look at the inner rim of the disk, but if you use ALMA or another millimeter facilities, you can have a full map of the whole wing, including the rotating disk and the wing that is escaping from it. Regarding the molecular content, it happens that this kind of objects comes in two flavors. There are cases in which most of the mass is contained in the disk, and there are cases in which most of the mass is contained in the wind, and we don't know what's the dichotomy. So one suggestion is that is related to the size of the grains. If you have big grains, you can really not push them away by radiation pressure. If you have little grains, you can do it. Maybe those guys with little grains or more content on little grains can release the winds, and those with little content of little grains will have less winds, and more the mass will remain more concentrated on the disk. I won't talk about the problem of the orbits and the periods because it's already addressed, but insist that this can be solved by the interaction with the rotating disk that we are observing. I'm going to talk about the red rectangle, which is probably the prototype, but this is the prototype of those that most of the mass is contained in the rotating disk. This is emission from PAHs. It's very faint, and there is very little mass in the well-known optical picture that we know from HST images. We know all the parameters of the system, thanks because this is optically bright, and the Hans and the team has measured all these things. But if you have a look at the molecular content, the view is totally different. Then you have the rotating disk, the blue part, the red part, and the outflow that is escaping from the disk, where we also see a little bit of rotation. That tells you that it's really connected with the rotating disk. And again, 90% of the nebular mass is contained in the disk. And if the nebular mass is contained, then the whole mass is contained that, because the molecular gas is the most important, the most massive component of these structures. Well, we did some, I'm going to show two ALMA observations. This is the ones that we already published. It was cycle 7. We reached 14 AU resolution for the continuum, 14 and 40 AU for the data because of the lower signal-to-noise ratio. Of course, that are much lower than the ones you get with optical near-infrared interferometry, but this is the best you can do so far in ALMA. This is the results for the CO, the 12CO, the most abundant molecule. I must say that these guys are also very poor in molecules if you compare with other post-AGBs, the ones presented by Carmen, or compared to standard AGB things. They are poor in molecular gas anyway. You see the egg-shape, you see the egg-shape outflow at some velocities, and then you see the rotating disk in the middle. You have a look at the PV diagram, then I guess you are convinced these guys are rotating. But they are not only in Keplerian rotation, you also need to introduce expansion. Without that, you don't explain these velocities, because if you want to have this large velocity spread at the center, then you need to put too much mass in the center, and we know what the mass of the system is. So we need to put expansion plus rotation. So this in fact are in sub-Keplerian rotation. We measure the outer radius of the molecular rich disk, and we can also measure a hole in the middle. That's because this is just a zoom in velocity of the same PV diagram. This straight line is telling you that there is an inner rim, and further in, there are no CO emission or little CO emission that we cannot detect. And this negative thing, at the beginning, we thought we were witnessing gas depletion on grains, but it's not. It's because the continuum subtraction, and because you always have a little bit of cool gas in front of your continuum, and then you get a negative control. So there is no hint of dust depletion on the grains, and that's normal because these disks are not so cool as the protoplanetary disk around young stars, and that's probably one of the main differences. Other molecules that tell you that the system is, the chemistry in the system is not this typical dichotomy carbon-rich, oxygen-rich. In this guy, we have detected H13CN, but there's also SiO, water measures, C3CH2, H2O, even OH. And I remember that the whole bipolar thing was plenty of PAHs. So you have carbon-rich things, oxygen-rich things. We believe that at the center, at the very center of the system, there must be something like PDR. Okay. Continuum. Thanks. This is the image you get from the continuum at 0.9 millimeter. You see it's a very flat structure, not symmetric. Is this a dust trap? I don't think so, but it will be great to be a dust trap, but not. There are two components, a compact component. I will show you that this is not dust, but that will come later. And we model that. This is the structure you need. Some more density in the middle. It's a flare disk, but more density in the middle. And the important thing is that this disk must be relatively opaque, even at 1 millimeter. The only way you can get that with reasonable masses is that you have very large grains. Otherwise, there is no way you can really have opacities around 0.3 at a wavelength of 1 millimeter. And that becomes even worse. This is from our modeling, this is what we get. And you can compare the data with the modeling. Of course, we don't reproduce these asymmetries. The disk is very compact. It's much more compact than the molecule, so there is settlement at the equator. That's precisely what you expect if you have grain growth, and it's also much smaller in the diameter size. Let's move out of ALMA, now go to very low frequencies. This is MeerKAT. This is just a point source. We only recover the flux, but you will see this is important. And these are the new observations from ALMA at 2.6 millimeter. Again, the same structure, the same asymmetry, and a little bit of warp disk at the very edge. These are not fully, these data are not yet fully reduced. But the important thing is that if you plot all these fluxes and you believe very old data from the BLA, from the 90s, you can separate two components into the compact component has a spectral index, which is characteristic of an ionized wind. That is precisely the wind that is escaping from the companion. And we can use these fluxes to derive a mass loss rate of the order of 10 to the minus 7. And this is the other one, the red one, is near 2. So it's a flat emissivity. So meaning that you need not only to have dust that is relatively opaque at 1 millimeter, you also need to have dust that is relatively opaque at 3 millimeter. And if, as I said, if you believe the separation that Jura did with the old VL data, then you will need to have even dust that is efficiently emitting as a black body at a wavelength around even centimeter or that sort. This, by the way, the pointer doesn't work anymore. There is a little star near the left axis. This is the MeerKAT flux, which really fits with the other fluxes we get for the compact component. So if you believe the separation, the problem with the red rectangle is not only that you need big grains in terms of microns. If we can get down there, we will probably need not grains, but pebbles or something that sort, because you need to have to be emitting very efficiently, even at wavelengths as large as 10 centimeters. And that's a problem. This is wrapping up. This is a summary of what we have obtained with the continuum. By the way, the mass we measure in these big grains is of the order of 25 Earth masses. That's probably the unit you want to use for this thing. And just as a comparison, there is no depletion in the disk, and the black contours are one of the velocity channels for CO. The other is the continuum. You see that the CO is much more spread than the continuum emission. And I think that's it. Thank you very much.
Thank you, Javier, and perfect timing. Any questions? Yes, please, Hans.
So with the ionized gas, you can derive the mass loss, and you obtain 10 to the minus 7 solar mass per year. And
but this is very crude, because I'm using your temperature, your velocities, but it's an independent way of obtaining this mass loss. It's simply the emission from the ionized wind.
Yeah. Okay. And can you estimate the uncertainty on that?
We need to run a model, because this is a very crude estimation, and the spectral index is not the right one, meaning that it's probably not uniform temperature. Obviously, the 0.6 is what you expect for constant mass loss, constant temperature, etc. So we probably need to model this radio continuum. What is important is that when MeerKAT becomes SKA, we will probably have maps of this, and we will probably have radio recombination line measuring excitation and velocity. But
Okay.
for that, we need to wait a little bit, I'm afraid.
Okay, thank you.
Yes, the other Hans.
Yes. Can I ask a question?
Yes, please.
Looking at the last slide, I mean, you have this very beautiful dust disk, but then we still have the X-shaped geometry. So can you summarize for the innocent astronomer why we have the X-shaped appearance? This is one question. The second question is, with so much big dust grains, is this a good example for secondary planet formation?
Let me start with the second. I'm not saying that this will be a candidate for secondary planet formation because probably time scale is too short. But if we want to look for these things or the formation of big bodies or relatively large bodies, that's probably the best candidate. And about the first thing, I was just comparing the dust at the same resolution than the gas because we got better map for the dust, but we don't play tricks here. And this egg shape is because simply because I am selecting one particular velocity, well, in fact, two particular velocity channels, one positive, one negative, and you see the effect of the rotation. So if I have plot the total emission of the CO, you will see mainly the disk thicker because the outflow, you must go farther away.
But in the near infrared images, it still looks X-shaped.
Yeah, that's reflected light. Yeah. No,
reflected light.
Yeah, but you see also this egg-shape thing. You also see that a much smaller scale because we are not sensitive enough, but we see the egg shape also in CO, no problem.
Okay, but it's not a dynamical feature, it's just reflected light.
No, in the case of CO, is emission. So we can measure the mass, the velocity, mass loss, etc. The famous picture from the HST is I think it's not reflected, it's emission from PAHs, but it's emission from PAHs, yeah.
Okay, we're going to take another question from another Hans.
Yeah, so it's an orange nebula. I didn't quite get it. What's the process for getting the PAHs there? And where in the nebula do you see the PAHs?
You see in the outflow.
Mm-hmm.
And I have no idea, but the point on the chemistry I want to make is that in these guys, this dichotomy of carbon-rich, oxygen-rich doesn't hold anymore. Because if you detect in the same source, at the very center, OH, water, but C3H2 and PAHs, then. But of course, interstellar medium is oxygen-rich, and they have all this stuff in the PDR regions, and they don't care.
Right, but it must have been produced somewhere. So
there must be a source of high energy photons at the center. The accretion disk, because we don't see those energetic photons, but from the chemical point of view, we have all the signatures of a photon-dominated region going on at the center. That's the easiest explanation for the chemical diversity.
Okay, we have some discussions over lunch, so let's thank Javier again. I will hand over to Claudia.
Yes, so as we already mentioned before, take the next 10 minutes if you want to review the abstracts, the talks, the posters. We will now show again the QR code for the voting. And let's say that we close the voting at 12:40. So please, we have a little prize for the best poster, best student talk, also best ESO VLT, VLTI results presented, and best ALMA. The last two are not only for students, but for anyone. Thank you, and enjoy lunch. It's served the lunch again, so you can sit again. No. We come back at 2. Please check if any of you lost a ring. We found a ring. I have it. No, 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 no.
Hello? Hello? Hey, everyone. We'll make a start for the discussion session number 2. I will be your chair, Taisa Danilovic. And if we could have the slides with the discussion questions. So let's suppose go through them in order. The first question that someone's put in the chat is, which data do we still need to confirm the origin of long secondary periods? Does anyone want to weigh in on this? No one? No data? Probably sensitive observations in the optical so that we can see the long secondary period if we're missing that. What else? Hans, go ahead.
Time series, no?
Yeah. Time series of what?
But so just high resolution spectroscopy, I guess, to get the orbits. It's only coming from binaries.
Yeah, well, maybe there's 2 classes of long secondary periods. Anyone else want to weigh in? Are we all sick of long secondary periods? At the back?
So I'm not exactly an expert, but for example, from the work of Benjamin, who presented earlier this week, so what he was mentioning many times is it'd be nice to have different timed observations, interferometric observations. For example, he was working on RTPAV, but he has only one period, and he was saying if we could have multiple, we could see whether the companion is actually moving, so it is a companion what we see, or not.
Anyone else have a comment on that? Or on anything else related to long secondary periods? Well, if we have 2 classes of long secondary periods, where would the division be? Because there are some that have very short, comparatively short periods, 1,000 days, maybe 2,000 days, which is in the realm of pulsation periods of the extreme stars. But then we have the ones that are years, which do seem more likely to be orbital. Does anyone want to comment on where there might be a division or not? No, okay, we're sick of long secondary periods. So, next question. Why don't we reproduce the orbits of post-AGB and barium stars better? What are we missing, with a few suggestions? So, are we completely missing a mysterious mechanism that we are not thinking of? Are we not describing the physics of the included mechanisms correctly? Is it related to the 3D nature of the stars versus the 1D nature of the models, or all of the above? Does anyone want to comment on that?
So I'll start, and then I'm sure there'll be lots of people who follow. So the recent work that Casper did, the Moltzler paper, they were able to, I think Hans was a part of it, they were able to reproduce the orbital periods with luminosity, but for low luminosity, the post-RGB stars, which are the low luminosity analogs. And for them, they had stable mass transfer as the mechanism, which is sort of what we always thought for these circumbinary disks. Now, what was interesting to me too, and maybe Hans, you might want to talk a bit about it, which was that for the post-AGB stars in the same sample, they did not see the trend with luminosity and orbital period. So is that to do with some sort of mass loss? Because it's the only thing I can think of which is sort of different. And then the eccentricities is a completely different thing. There, I think we are not describing the physics properly, is what I think with eccentricity. It has something to do with winds or pumping, but we just don't know how to describe it. But maybe I'm curious also to understand why for the post-AGB stars, we don't have the periods.
I think so. The RGB, so the post-RGB are in fact very similar systems. They create a disk, but they are expanding in the RGB to such an extent that you have the interaction already on the RGB. And then the evolution is then very similar. And in fact, what you see is, what you assume then is that the period is directly related to the Rho slope, and hence the radius of the star when the interaction happens. But then you go to the HB, and that's much more fluffy, and then you have a much more diverse sample. Yeah, yeah, because the envelope interaction is really dependent on the AGB when that happens. And so if you have a thermal pulse, for instance, they increase in radius, and then you can have an interaction. While on the RGB, it doesn't happen. It's just the star that grows until a certain radius. And AGB is much more volatile in its radius during the AGB evolution.
Yeah. So then what's the spread in the original, like pre-interaction orbital configurations?
Yeah.
What's the spread there?
We don't know.
Or what could it
we
be?
assume that we lose some of the objects because they spiral in, but we don't know which fraction is really evolving towards what we see. So that's a sad answer, but I can't help it for the moment.
You use the microphone, Devika.
It would be the slightly more massive, like 2 solar masses, a 2.5 and above, because which don't do post-RGB. Yeah.
So the radius, but Lionel will probably comment. So the radius increase of a lower mass star is much larger than for a higher mass star.
I confirm that. But the problem remains with the eccentricity. This is really the major problem. We tried different things. Particularly, there was a hope that if you have a circumbinary disk, then you would have resonances, Lindblad resonances between the disk and the binary, the two stars inside. We tried well with a 1D code, but it's not sufficient to produce eccentricities. The observation do not, well, they show eccentricity where our models predict circularization. But actually recently it has been a very interesting proposal to explain these high eccentricities, some kind of quasi-Lidov pumping. So a misalignment between the orbit of the inner binary and the inclination of the circumbinary disk. So you would have some exchange of between inclination and eccentricity that will eventually produce these short period eccentric systems, and eventually when the disk dissipates, the system remains in that state. That's a very interesting possibility, because we've tried many things. Because when you transfer mass in an eccentric orbit, you also can generate some eccentricity, just because you transfer the angular momentum at different phase along the orbit, and this is not spherically symmetric, so you introduce some anisotropy, but that is not sufficient. So we have to invoke something different, and it's something that is new, this quasi lead-off mechanism that could help better understand or maybe reproduce the eccentricity of those systems at shorter orbital periods.
Ton had a comment?
But then in this case, there is another question why disk was formed not in the same plane as the binary orbit.
No, I cannot answer everything. Huh?
Lionel pretty much answered everything I wanted to say. So.
Anyone else want to comment? You can also jump in if you have a microphone. Otherwise, wave your arm a bit. Oh, well, maybe let's move on to, do the circumbinary disks form already on the AGB, and where are they? Yes, around L2 pub, but yeah, Hans, go ahead.
But maybe they are created at the end of the AGB. So they are the cause of the end of the AGB is the creation or the interaction that creates the circumbinary disk.
Disk is the process of making the disk starts in the AGB or the RGB, wherever you start filling your Roche lobe, and then you go into some sort of stable mass transfer. But by the time you form the disk, you should be off the AGB because you would have lost the, well, in L2 PUP it's different, but it's the only system, right? Is there any other system in the AGB phase or RGB phase that has a circumbinary disk?
Well, there are some indications in some of the ALMA maps for other sources, but they are not so well constrained as for L2 puppies. So I have to admit I do not agree fully with what you say, that it should be at the end. Not then from the modeling perspective, also with some caveats there. The main mechanism you need for a disk to form is cooling. And when you have enough cooling, you can, in the models, you can do disk forming. There are many uncertainties when it comes to cooling prescriptions, but without cooling, we cannot do it. And so there are some simulations, for instance, from the group of Blackman et al., that do show the formation of the disks around AGB stars.
Is it like circumbinary disks are different? Like you've got different properties? Because like L2 PUP systems, orbital periods are very different to post-AGB binaries. They're long periods. So could
L2 PUP is maybe not circumbinary. The companion seems like it's in the disk maybe.
Well, there have been simulations for a circumbinary disk by the Chen group.
Yeah. It's in, yeah, I've always thought of it as a circumbinary.
Well, so also, if the disk forms on the AGB, why is it not blown away with the dust-driven wind?
That's, yeah.
Stability is also a good question.
But the orbital periods are very different for the two systems. Like the post-AGBs are quite long periods, and L2 PUP, if at all it is, it's a short period.
But we numerically define what we think short and long period is, just for context in the room.
Well, long period would be 300 to 1,500 days. Short period is more like, I don't know, less than 100 days.
I think that's what you're. But the post-AGBs don't have less than 100 days periods. No.
That is a problem. Yeah, not the post-AGBs, no.
But then it's a bit similar to what we see in the young stellar objects. That's dependent on some parameters such as luminosity, which for us will be critical. If the luminosity increases, I have seen also outcome of simulations where we indeed can see that the disks are going further out and that there is also a sublimation of, mass loss from the disk at the outer side. And this is the young stellar objects, but as you have been arguing, it can be the same for our AGB towards post-AGB stars. So We haven't done the simulation since the timescales are so long, so we really would need to do some snapshots. But it doesn't feel too much as a concern to me, but prove me wrong. Eh?
So there's a paper, a few papers apparently coming out from students of Ursula DeMarco and Jack Nibbs, so maybe we should look out for it. And in that, the simulation is forming the circumbinary disk around post-RGB stars. And from my conversations, again, private communication, it's basically that the disk, when the disk is formed, the stars are already off the RGB because but this is again fully constrained with the post-RGB, post-AGB parameters. So maybe the question, which is what kind of circumbinary disks, they could be different, as you said.
Is for you, how do you define what kind? You mean Keplerian versus subkeplerian, or how should I understand the question?
Like orbital parameters, like orbital period, eccentricity, what's the stellar binary in the middle looking like? You know, if you have like a white dwarf companion versus a main sequence companion, the mechanics becomes different.
It's not mechanics, eh? If you have the same mass. It's a bit of the UV radiation, and then we have to look to Marie, and they're having the impact on the molecules. But it's mainly the mass and the separation that dictates it. Theo.
So one thing that I be thinking about while you're talking is several people brought up this thing that the close companion will increase the mass loss rate of the AGB star, but a direct consequence of that as well is that it will decrease the lifetime of that star on the AGB.
Yeah.
So it might be that we have a lot of selection biases that we see that we have much more AGB stars with lower mass loss rates just because they stay in that phase longer. So that might be a part of the problem.
Well, also that means stars without a companion that don't have their mass loss rate enhanced are going to have longer AGB lifetimes and have more time for nucleosynthesis, which, you know, does other things, chemical evolution, blah, blah.
But another thing that I wanted to add is that one thing that confuses me a lot is that when I think about the objects that Carmen was talking about today, these very obscured post-AGB stars, I thought I had a very clear picture that those must be post-binary interaction systems in which a lot of mass was ejected at the same time. But then Hans Olofsson is looking at these bulge objects, and then he sees these extremely obscured objects in his sample. And I was convinced that those would be these post-interaction systems that we see as well in these post-AGB stars. But we can fit that very well with just an increasing mass loss rate over a few thousand years from what we think are clearly just AGB stars to those post-AGB stars. So that made me very confused about what is actually happening. It seems like we don't really have these two classes, one that goes through these very violent interactions that a lot of mass gets lost at the same time, but it's more of a transition, and that really confused my happy, simple picture.
But yeah, Carmen, because your object is still an AGB star, isn't it?
Yes, the object, one of the objects that I discussed this morning, it is actually an AGB star, okay, and it has a rotating circumbinary disk, but it's a complex object, and maybe it has involved a triple system, and this is something that we are coming back more often to as an explanation also of multipolar preplanetary nebulae that have even bipolar winds that are orthogonal to each other. So I'm wondering if maybe we need to add this extra complexity also to the models that predict how the orbits evolve. Maybe it's not different. I mean, not easy. And I was also wondering what is the effect of, for example, adding magnetic fields? I mean, how this can affect the accretion and impact somehow the orbital evolution as well. I don't know if the people that model this are considering including this effects or maybe are totally negligible. But for example, triple systems are not that, I mean, I think it's 30% or 20% of the systems are triple. So maybe we should start considering adding this extra complexity to the models. And also in the case of coming back to OE 231.8, which is the AGB star with the main sequence companion, the disk is still there, and the mass loss rate at present is not that low. It's apparently 10 to the minus 5 solar masses per year. It was much higher in the past, but then there was even an older epoch where it was much lower. So it's, you know, it's not following, maybe not all of the objects are following just the standard evolution as we think of it, no? Just an increase at the end of the AGB and then a drop. Maybe they are doing other things.
Or was it an eruption in the past, perhaps?
Sorry?
Was it an eruption in the past where you said a higher mass loss rate?
Well, what we find around this object is a very extended halo that it's indicating a mass loss rate of about 10 to the minus 6 solar masses per year. Then, of course, the mass loss rate that you derive from the main large-scale component is 10 to the minus up to 10 to the minus 4 solar masses per year or so. And then at present, there are indications that the mass loss rate has decreased to 1 order of magnitude relative to the other thing. So,
and the rotating disk, it's not expanding at all? And
the
why
disk is expanding.
Oh, it is.
The rotating disk, the tiny one that we are finding, well, it's a circumbinary disk. It's rotating and expanding very slowly, by the way. I mean, both the rotation velocity and the expansion velocity are 3-4 kilometers per second.
So does that
very low?
That doesn't match the orbital velocity?
It is lower. Yeah. Yeah.
The
The orbital velocity, if what we guess from the orbit is correct, is like 8 kilometers per second.
It's similar values and for Hydra, but it's not so well constrained as in your case.
Yeah.
Javier, did you?
May I ask a question about the masses of the circumbinary disks or the disks for Kamen's objects, and then in the ones that are having in the AGB? Because I'm just trying to think if there's a how they relate across the different phases.
Well, for our objects, there is only one. I mean, the high momentum, or cases like OE 231.8. The mass of the disk, of the rotating disk, is a little bit uncertain because we don't trace the whole disk. We only trace the upper and lower surface of the disk. But it's probably, I think, our numbers, considering the emission from the salts and also from the dust in the disk, is probably 10 to the minus 2 solar masses or so.
Okay.
Don't remember very well, but I think it was about that. Yeah.
Javier?
This 10 to the minus 2 is pretty much what we get in all these post-AGBs, which is again a problem because we only see the disk. We see a little bit of outflow, where all the mass that has been lost by the post-AGB is nowhere. You cannot find it. That's a big problem because in the other cases, in the monsters, you have the eruption, can be up to 1 solar mass, that explains the evolution. Sometimes you see this bipolar ejection inside a very dusty cocoon already. That means that the post-AGB reached this post-AGB after a long evolution in the AGB phase. So you were at the tip of the AGB, you have a very heavy wind, and then something happens, you release the jets. Some other cases, you don't see the heavy envelope, but you still see a fraction of a solar mass ejected somehow that accounts for the spectral evolution of the target. For the post-AGBs with the combinatory disk, the mass lost is nowhere. We don't know how to find it.
But isn't that the gas mass? Sorry. Isn't that the gas mass, Javier? So you could have dust that is somewhere settled.
Well, then we need to multiply this by factor 100. If we can have 100 more mass in dust than in gas, that's the answer, Bert.
Which is, yeah, 0.1 is not.
Yeah, it's very little, and there is no ionized gas. There is no trace of anything in this post AGB binaries with
And
clear.
how do you measure the dust mass from the outer envelope?
You can estimate. I mean, from the continuum, you can estimate assuming some properties for the dust. Of course, if the properties of the dust, if the big grains becomes very big.
That's
But
it.
then again, you have a limited amount of metallic elements. And then the problem will, what is the light elements? The ones that go into CO and other stuff. There is no such amount of gas.
But at least for the first point, what you can see in this kind of simulations is that the gas and the small grains are coupled and they stay in the disk, while the big grains, they just feel the radiation pressure and they just fly out. And I remember from a simulation for L2 puppies that this was exactly the case, so that we had this, which you expect there. So you plan your Epstein regime or you calculate your Stokes parameters, and you can see that the small grains are coupled to the gas. The bigger grains, are not coupled, and they just feel either the radiation pressure on them or the gas pressure gradient, and boop, they are gone. But so this hypothesis would imply then that you have mass in big grains, which are maybe then more difficult to measure.
Yep, but again, I mean, where is the H2? Where is the H2? Because,
Or maybe
most of the stuff must be in H2, H1, or whatever. That's most of it. And we don't find it anywhere.
If you're saying the gas isn't ionized, perhaps the dust is shielding it?
There is no ionized gas around.
Yeah, but the dust
Yeah,
is
well,
blocking the light maybe?
Maybe we should wait for Meerkat and look for H1. I don't know.
Yeah. Tom?
In relation to the expansion velocities found for the disks, can you use that to infer the viscosity of the disks, for example, using viscous evolution theory? Because that's a huge unknown in the fundamental parameters of the disks, also in relation to structure formation and planet formation and that kind of thing. No. In general, just for the people that measure and know about expansion velocities in the outer disk regions, can that be related to viscosity somehow? Or is that a possibility?
No.
No?
We have even for liquids, we don't have a good feeling on viscosity unless we can measure them in the lab. So I'm really skeptical. I might be wrong, but I'm really skeptical we have good well, we can just use some typical values, but.
If I remember correctly, the viscosity is also important for the eccentricity pumping, no? Like there were some hydro works in which if the viscosity is too high, the eccentricity does not pump up at all. So measuring that will also, or the other way around, I don't remember, but it's important. So another reason to measure it if it's possible somehow.
If there are no more comments on circumbinary disks, maybe we can go to the next slide. So the next question is, how can we link AGBs in binary to post-AGBs in binary in the next decade and or before the next YAGB meeting? Yes. I mean, maybe the first question is, when will the next meeting be? Will it be in 4 years again, or? Yeah.
It's something for the so the next meeting is something for the end of the conference.
Actually, Theo and I were having a chat in one of the coffee sessions, and he suggested really connecting the binary interactions across all the binary channels, and something that Hans and I have also talked about is probably something we need to do through, a combined effort, because it's not something one small group does. And I think that kind of goes into answering this question, because there's so many different sorts of, like a zoo of binaries, and this is all across, say, the evolved binaries, and how or do they connect? And what is the binary interactions that connect it? So we should probably think of a combined effort to answer something like this. Maybe Theo suggested ERC, what was it called again? Secretive? No.
I'm tired.
And
I think the way forward is Gaia DR4 and combining that, if we get time, with ALMA. Since then you can have your masses, you can have your orbital solutions, and we know all of the ERP diagrams, but we are missing there the information of the AGB source. And this is what Gaia DR4 will be able to do for a significant sample, and that at least it's still diagnostic, but at least it will give us observed parameters that we can use to benchmark our binary evolution codes towards.
I don't think Gaia DR4 will give you the AGB orbits or most of the barium star orbits, at least.
It will.
It will not go longer than 2,000, 3,000 days, and we have orbits up to decades.
But for the AGBs, we have none.
Yeah.
We have one. Now we have one, an 11-year period.
Yeah, no, I mean, basically that is going to cover the short period range. I mean, it's still useful, of course, especially if we can link the populations, but it will miss a significant fraction of the objects. I think, I don't know what are your periods, post-AGB people, but also higher than 2,000 days, right? But yeah, still, any orbit is useful, no?
But I think also not only finding the binaries, but characterizing them as we have seen yesterday, I think, with these high angular resolution observations. And also, I think, I don't know who is working on that, but determining if the companions are white dwarfs or main sequence, that would be really helpful to clarify some of this orbital evolution.
But then we bring the chemistry into it as well. And with W Aquila, we have the 1,000-year orbit constrained with chemistry.
Yeah, and this is also what Julien has been doing,
Yeah.
Using other types of data that can help us pinning down whether it's one or the other.
Yeah, but there this flickering observation as well, which I know basically just a name, like this visible light flickering that people use to determine if the company is a white dwarf or not. Maybe people should do more of that once we have a better zoo of, or a better sample of possible binary.
The math can help too, unless you are very unlucky and you have the perfect 0.6 solar mass main sequence star. With the mass, you can also guess. And if you combine radial velocities, astrometry, and all the stuff that we have, you can get a decent constraint on the secondary mass as well.
You can also use very long frequency radio to characterize some of the companions if they're at the right separation and the right type. Just saying. The next point is following on from the one we've just been discussing, which is also how can we link AGBs in binaries with the more evolved progeny, like the orbits of the BA stars, and the post-AGB binaries are statistically different, so is the chemistry. Related to what we've been talking about, but does anyone have more comments on this?
I put the question, so I cannot have the answer. So don't look at me. Saw the previous one and I just reacted to it, but I don't have the answer. I've been discussing this with Hans for like, 10 years now, so.
If no one else wants to comment on that, perhaps we move on to the next one.
No, but
No?
can maybe someone quantify what it means? That the orbits are statistically different? I mean, I know we heard about that before, but...
Yeah, the log-P diagram of the post-AGB binaries is more like a square. So like you have the similar eccentricities across the whole period range, while the barium stars have like an envelope that goes to higher eccentricities at longer periods, which you could think that it's because as the barium star ascends the RGB, so the second RGB of the system, tides trigger again. But if you look at the orbits of the barium dwarfs, where there's not been a second RGB phase, they are statistically the same as the barium giants, but not the same as the post-AGBs. So there is a difference in the orbits between the post-AGBs and the barium stars in general, even though they are the evolution of one another, and there is not been a major significant event there. So, but the chemistry is also different. So it is possible that the barium stars are a different family. They go through a slightly different evolutionary channel than the post-AGBs, but then which channel, that we don't know.
Any further questions or comments on that? No? Okay, then we go to the next point. We see that we certainly have a high proportion of AGB stars with a companion, especially with my talk. We might have dust enhancement induced by the binary companion. Then how much does this bias our dust to gas ratio estimation and then impact the real mass loss rate of the main central AGB star? Could we have a global overestimation of the mass loss rate for AGB stars? I will start commenting. So I think mass loss rates from CO, when we don't have anything too dramatic going on in terms of like being not spherical, are probably pretty good most of the time. When we have the mass loss rates from dust instead, then there's more uncertainty if we're getting the dust to gas ratios wrong. So perhaps the dust enhancement, which is increasing the amount of dust relative to gas, is part of what's causing, you know, the really high mass loss rates that we get from dust modeling for the extreme OHIR stars, for example, and perhaps solves the problem of the, you know, those mass loss rates being above the single scattering limit, that kind of thing. So I think it is changing the dust to gas ratio. On the other hand, that doesn't mean the CO mass loss rates are wrong.
Well, I think both are wrong. You know, it's also not only the dust, so Davide has shown it as well. So it's indeed a dust formation in the spiral arms, for instance, but it's also the fact that we will have more of the dust into the equatorial density enhancement. And that is exactly where the temperatures rise around 1000 degrees, 500 degrees, for it to peak around 1 to 3 micrometers. And this is also another cause why this dust mass loss rates are too high. So it's not only the new formation, but it's also what is happening in the equatorial density enhancements. And then for the carbon monoxides, they are okay if you measure them. Also, I agree with how Hans Elofsson has been doing that. They are okay-ish if you measure them, you know, with different beams and then convolve your simulations with your beams. But even then, you might have an estimation of a binary and not of a single star. So it does not imply that the CO mass loss rate that you get is one for a single star if we...
Oh yeah, definitely not. No, sorry, I mean, they're roughly correct for the objects we're looking at, so long as they're not weird shapes.
Yeah, but we have to follow the...
They're all binary.
Yes, we have to follow the procedure that Hans has also been doing. Do that for different angular...
Well, and also different energy CO lines, right? Absolutely. It's sad that we don't have Herschel Hi-Fi anymore.
Yeah.
It's
yes.
Unfortunate.
Yes, absolutely. Yeah.
I might, sorry, just to respond to that, because it's been confusing me since you presented it. So not you personally, but you just said it also now. So to me, whenever we use CO lines to estimate mass loss rates, I mean, we are making an imperial measurement of the mass that is lost in the system. So the star is losing this mass. And we have to be careful that we don't conflate this with the mass loss mechanism. So I agree to you totally that, so this single star is indeed losing this mass. It's just caused by having a binary companion. So we can't translate that mass loss rate to what a lonely star would lose as well. But the mass loss rate estimate is well, as correct as we maybe currently can do with CO
Yeah, I agree. What I wanted to say is that we have to be careful with the mass loss rate relations that are derived from the gas mass loss rates and that are put in our stellar evolution codes.
Yeah, I
Because
think
how, what I would recommend, and I don't know whom asked, I think it was an online question, is a safe estimate potentially while we're working on the problem is taking somehow the lower limits of what we see in these relations and assume that the upper part is potentially scattered from binaries. And that might be a safer proxy while people are working, into diagnosing better which ones are single or binary stars.
Yeah, I think that's fair enough. Yeah.
I think also what we're like empirically determined to be an average mass loss rate, which is somehow related to what goes into these stellar evolution models, is average for what's mostly binary stars, because these are the brightest ones. These are the ones we've studied the most. Whereas the single stars probably have lower mass loss rates, but we're not studying them as much. NES will hopefully help with this. But when you have a single star stellar evolution code, you should be using a lower mass loss rate to study single stars. And yeah, I mean, there are implications for stellar evolution with all these mass loss rates, as we've said a few times now.
But, sorry. But I think we have to be careful not to get into the trap of thinking that every high mass loss rate object that we see must be a binary as well, because we don't know that, right?
No,
And
but yeah.
in the sample of Hans, again, Olofsson, he said, sorry, Hans. I expect to see this in the summary. So in the sample that he's working on, the objects were selected from a OH maser emission, right, Hans? And he models them and he finds very high mass loss rates for all of them. And I have a very hard time believing that all those objects have binary companions, enhancing those mass loss rates. So
But
I
they
think we
are
have,
all at the end of the AGB, right? So that's a slightly different situation.
well,
Or
but
mostly, aren't they?
But I think there is a distinction there that yes, objects will have potentially enhanced mass loss because of companions, but there's also a mass loss rate evolution during the AGB, and we have no idea what the timescales are between these two things. So it's very risky if we start sorting things out just based on the mass loss rate that we see, I think.
There is a trend with pulsation versus mass loss rate, right? As we've seen a few times. And so higher pulsations, it makes sense. They make more dust. We lose more mass. So that is sort of another contributing factor, like related to what Theo has just said. And well, perhaps also the carbon stars that end up having high mass loss rates and, being carbon stars and having large pulsations, maybe they are more likely to be single stars because they've lasted long enough to become carbon stars instead of losing mass more rapidly earlier in the AGB. Maybe.
Actually, one thing that I think I've again learned at this conference is something that Marie, I think it was you. Yeah, you pointed out in her presentation, and that is that we have to be really, really, really honest with our uncertainties. So instead of drawing sweeping, generalizing conclusions, no matter how much we would want to say something so fundamental about evolution, we maybe have to just acknowledge that, yeah, well, this mass loss rate might be affected by there being an undetected binary companion or some other process. And maybe the dust mass loss rate I'm determining, it's just the dust budget that isn't actually lost from the star. And I think we can be confident and include this simply, and maybe I think a lot of us do, but just to remind ourselves that it's just uncertain. That's why we have these conferences, right?
Elvira, did you have a comment? Oh. Anyone else?
There's an online comment by Ian McDonald. We should be able to assess whether the mass loss rate is globally overestimated by using the initial final mass relation, the number density of AGB stars, and the modeling MLR from stellar evolution models.
You can unmute yourself, Ian. Perhaps you can expand on that a little bit more.
We know how much mass loss stars are exhibiting because we have the initial final mass loss relations. So we know that we know how much mass we need to lose. It's just a case of when. So if we can match that up to how many dusty AGB stars there are and see how many we expect from stellar evolution models, then we should be able to see whether we have any kind of systematic over or underestimation.
But then are we looking at the right systems for the initial final mass relation? I mean, are we looking at systems that had some sort of more dramatic, exciting interaction, and that's why they're already cool white dwarfs?
But we're usually looking at single white dwarfs in open clusters to get the mass. So we should have a fairly low binary fraction there anyway. And if there isn't, then we should see some kind of distribution in that initial final mass loss relation if binaries have an effect on the total mass that's lost.
But so something that I don't understand very well in this respect is, do we expect the core mass to change very significantly during the AGB? I thought that that was relatively small change. So does the mass loss rate at the AGB affect a lot the final mass of the white dwarf?
Yes. The longer the AGB, the larger your core mass will be.
No, but I thought when they enter the AGB, the core mass is almost the same as it will end up being.
It still grows during the AGB. Pretend Amanda is here saying this.
But it's a relatively small amount, right? Or?
But that depends on the dredge up efficiency, which is unknown. So you can get whatever you like.
We should quickly look at the next slide because we're running out of time. Sorry. Oh, Mikkel, quickly say something and the slides can change.
Just a very quick comment. Maybe a naive question, but shouldn't we see like two populations of stars that are binary and non-binary with systematically different mass loss rate in this case?
Perhaps
maybe
we do.
Tiny.
I will quickly answer to this. This is actually the topic of Jaime's thesis. We were trying to compare the properties of binary AGB binary candidates with larger samples of AGBs, right? The problem is that it's very difficult to know if an AGB is really binary or isolated, but we chose these X-ray emitting or UV excess AGB stars as candidates for binaries, and we studied them very in detail through CO emission to characterize the circumstellar gas, and also we're doing the dust, and we're doing also some chemistry, but we don't find really very different properties in the mass loss rates between the two samples. I mean, we put them in all kind of diagrams and they fall exactly in the same place as the others. We don't know if this is because there are no differences or because the larger samples of AGBs are also contaminated with a lot of binaries, but we are not finding like really different trends. Maybe slightly different dust to gas mass ratios, but it's not totally, it's not something like super clear.
Thanks, Carmen. Can we quickly have the next slide? Yeah, okay, we're not getting through all of these questions. It is pretty much time to wrap up the discussion session, but if anyone has any final thoughts, now is the time. On anything, doesn't have to be this slide.
Yeah, so we were discussing together with Pilar that it's not only the amount of mass loss, it's also the chemical composition of the mass loss. And in that respect, it would be very important to have more constraints on the third dredge-up luminosities, depending on the mass and on the metallicities of the stars. And well, here spectroscopy is very much needed. And concerning the last question, I would suggest that by the next YAGB conference, we all put in each of our paper somewhere hidden, if you want, because I think ChatGPT is very good at looking for hidden text, that S-stars have C over O between solar value and 1. And by the next conference, we check if ChatGPT is a little bit wiser.
Ah, and here is Hans, just in time for his wrap-up session.
Well,
Conference summary.
can the other Hans still raise a question?
Go ahead.
Because it's the last but one point in this last slide that you that I have highlighted. I mean, it's a question of how we can relate the AGB evolution to the, which I would call strongly or graphically, the death of planetary systems, you know, and whether the AGB wind, when it overruns supposed planetary system, what might be the observable effects that maybe ALMA can detect. This should be, for me, that should be a very topical question in the future.
Yeah, something for us all to keep in mind going forward. Now, Hans Olafsson.
Okay.
It is
thank you.
time. Your conference summary. Guys.
Thank you. Yeah, can I so put this here if I need it? And then I need these.
Oh, get up.
Yeah, my old friend. Can you hear me? Okay, very good. Oh my God. So yeah, let's go with the conference summary. I thought I'd just start with two observations, one news advertisement and one advice. And the two observations is that I think it's very good to see that we have such a good gender balance here during this conference. Really, I'm impressed. I think it's also good to see there are so many young people attending the conference. That gives some hope for the future. And then, of course, we had the advertisement of a new incarnation of the AGB newsletter is really on the horizon. And I think this attracted the highest applause during the conference. And then I have one advice, and that is never accept to give the conference summary. But of course, I've been SOC chair of this conference series for 4 times, so I felt some pressure, I have to say. So here you can see the four previous versions of this conference series, and this was really an idea from the beginning, the brainchild of Franz Kerschbaum, Josef Ron, and other people in Vienna, and I joined them as SOC chair. And it materialized in the first meeting in 2006. And then it went on and culminated, I would say, with the IAU symposium that we had during the General Assembly in Vienna. It's very strange, you know, we started in 2006 in Vienna, and then every 4th year we had a new one. And then suddenly, we get the General Assembly in Vienna, also 4 years after the next one. Yeah. Okay. And now a little bit later than that, I mean, it's actually a stretch of 7 years, like we're here in Santiago having the 5th incarnation. Of course, we have had the pandemic in between and everything. I thought of asking the question, how many attended all 5 conferences, but we already have the answer from Martin's first talk. So there are 5 of us that's been there all the time. Or, sorry? On the Monday, there were only 5.
6 on Monday.
Okay, yeah. Okay. Yeah. Okay, constrain yourself, son. So there's one thing. I mean, we're not a very big community, really, and it has become a tradition that we remember some of our colleagues that we, of course, met over the years, become very good friends with, and so on, and that have eventually left us. And this time there were 4 of them. So Paula, Inma, Roberto, and Carl, and we had some very nice sort of obituary talks on the first day. And of course, these are people that all made substantial contributions to the research on AGB stars, so, but are no longer among us. All right, so these are the themes of the conference, and in my summary, I will not exactly follow these themes. I will do it a little bit differently, but I'll come to that. So what I've done, I've looked at the 2006 proceedings and to see how things have changed since then until 2025. That was the starting point. And that was my primary idea. I think in the end it failed completely because the 2006 doesn't really play that much role any longer. But I thought it was an interesting way to look at it. And then I have to say, I'm really not an expert on most of these topics. So if there are any misunderstandings, I'm sorry. And if there are major ones, please just interrupt me and correct what I've said. Of course, I cannot mention everything that's being said here over the 5 days. So apologies to all of them who feel that their work has been left out. And maybe you should take some. I forgot the English word for that. Never mind. But with my limited insight, of course, I will surely miss things that in the future will turn out to be of real major importance. And maybe then you will be happy again when you see that will happen. And I'm really sorry that I have not really had time to digest this and put it into a more entertaining and insightful presentation. And of course, especially for the final day here, that to summarize the talks on the fly, more or less. So second, apologize for that. I will not have space or time, I would say, for figures or mentioning names, etc. And you are all excused if you fall asleep because you find this too boring and too lengthy, I don't know. So my first theme will be stellar structure and nucleosynthesis, and this was really something that was extensively covered in 2006 and of course been covered here as well. So I pick up the things that have changed in that. There is clearly an extension of parameter space now, looking at very low metallicity up to high metallicities and structure and evolution models for that. Yields of S-process elements have been updated in that. But then there remain quite a number of uncertainties, actually. Is the uncertainties in the third dredge-up, I mean, the mass limit for third dredge-up, mass limit for carbon stars, the efficiency, and so on. There remain many uncertainties in the possible extra mixing processes. And we've added the complications of binaries, for instance, that will also may have an impact on composition. The I process was not mentioned at all in 2006, but it's something that come up over the last year. And so that is an important process. And I'm not sure if I got it right, but it may be the explanation for the J-type C stars, if I get it right. And these are, the proper J-type J-type C stars, the ones with very low 12C, 13C ratios. So. And then, of course, we have the pre-solar grains. I always find it amazing that we can find this evidence of AGB nucleosynthesis on our doorsteps, essentially, and the accuracy to which they can measure abundances and so on. So continuing then, also, of course, 3D was not available in any way in 2006. And we now have these very impressive and realistic 3D stellar models with convection, pulsation, dust formation, and so on. But it's horrendous. It takes 6 months for a model. I mean, imagine we have a YAGB 6 in 4 years, and Bernd will be here presenting 8 new models. It's unbelievable. I think the conclusion for that is that 1D models will continue to be very important, really. And related to this is, of course, can we start to predict mass loss rate from first principles? I don't know. I mean, it looks like the results are very dependent on the details. We saw, I mean, only changing the period a little bit leads to very different mass loss rates. And then we have the complications of a possible companion. I'll come back to that later on. And then we have the traditional stellar atmosphere modeling of spectra, and this was really extensively covered in 2006. And there were discussions on the pros and cons of different codes and so on. This time it was much more focused, I would say. We didn't really think there were any issues with the stellar atmosphere modeling, and we looked in particular on S-element estimates and of course the special role of technetium for studying the third redyap. And it's interesting to have this dichotomy of intrinsic and extrinsic objects that gives kind of extra dimension to it. And of course we have this plethora of very different extrinsic objects where the memory of an AGB wind has been imprinted. And in this context, there's a huge increase in the number of objects since 2006. We heard about something called a Gala survey, where 1 million stars boiled down to almost 1,000 barium stars, for instance. And then it was mentioned the ability to do cosmochronology and also estimating the temperature in the S process region. I hope I got the elements right here, but... Right, and there was this emphasis, of course, that S stars are not the same thing as a C over O equals to 1. They actually fall in the range 0.5 to 1, and only the SC ones are close to 1. And then I also learned that they are technetium-rich M stars, so they've gone through thermal third redyap, but have not turned into S stars. So that was new to me, but apparently been known for some time. And there are also this remaining puzzle of the process behind lithium-rich giants in globular clusters. Right, so then to the importance of magnetic fields. This was discussed to some extent in 2006, and primarily its dynamical importance and so on. But in 2025, there really haven't been a focused discussion on magnetic fields. I've just heard things like magnetic mixing, magnetic mass ejection. Of course, the ionization degree of the AGB atmosphere is crucial here to get the coupling to the magnetic field. And there's jet formation in accretion disks in binary systems. So a few scattered things. There's only one measurement reported, and that's the magnetic field strength on the surface of a red supergiant. So this is an area where there remains much to do, I would say. And then we have the multiple period luminosity relations and their interpretation. This was really barely covered in 2006. But now we have these multiple period luminosity relations and their interpretation in the form of pulsation mode sequences up to the third overtone as far as I understand. And this is well established and confirmed with stellar structure modeling. Maybe also in the 3D models, but I wasn't 100% certain that I understood what Bernd was showing there. And then we have these intriguing long secondary periods, which about a third of the AGB stars show. And my understanding that they are essentially only semi-regular variables. But one can, of course, ask whether there is an observational bias here that we're actually missing. The large period mire us and it's difficult to see it. There's a discussion on the explanation here. Two phenomena were suggested, either companions or oscillatory convective dipole mode. So maybe there is both. I mean, the future maybe there will be both. There are, in fact, in action. Only the future will tell. There was also an interesting suggestion of a better physically or chemically anchored classification of the long period variable. That's a very valid point, I have to say, because the classification as we have today is odd. I mean, you could certainly have a star that could be a Meyer one environment and then a semi-regular variable in another environment. But are we willing to reclassify all stars that we've looked at and so on? Maybe now is actually the time before we get this enormous number of new objects from the Vera Rubin telescope, for instance. So I won't do it, but hopefully someone will do it. All right, and then I picked up this, and then I was interesting to see that Martin has also picked it up, because this was really not in the program, AGB stars as distance indicator. But it is an absolutely interesting topic. And of course, their role in resolving the Hubble tension makes us proud. Now we're at cosmology level here. Now, but that's clearly more to come here as the method matures. And we probably like to have more observations on these types of objects in more galaxies and so on, see are there metallicity effects, etc. Can we calibrate it away and whatever? And then we come to the use of interferometers and in many wavelength regimes producing high angular and also high spectral resolution data. And in 2006, there were very few interferometry talks really. And that's absolutely changed this time. I mean, now we can resolve the surfaces and atmospheres, not of all AGB stars, but the most nearby for sure. And we can do it also kinematically, so actually see how things move in the atmosphere of these stars and measure inflow and outflow velocities. We can measure atmospheric gas and dust distribution, also for the same object, and measure convection characteristics. And I also find that the radio photosphere phenomenon is sort of an interesting probe of atmospheric characteristics. And we heard about the presence of hotspots. I guess probably probes of shocks. One of the things which I think is really a unique possibility for AGB stars is the possibility to characterize gas phase species that are potentially involved in dust formation. And another thing that I thought about when looking at all this interferometry data is that we have to remember at all that we do not always need a high resolution. So there are, for instance, good arguments for a big single dish for millimeter, submillimeter observations, when we only need the sensitivity and don't want to miss any extended flux and so on. And I guess the same argument goes for other wavelengths, really. One thing to note is that this image reconstruction from optical interferometer appears to be a very tricky business, although there are suggestions now that there is a pipeline. Be interesting to see. Of course, more baselines will really make things more reliable. We have also seen a number of cases here where the focus has been on the detection of companions around AGB stars. And this is, of course, a natural thing to do because there are so few direct detections, and we use them more and more often to explain various observed phenomena. That leads me to, are you still awake or, yeah? That leads me to circumstellar envelopes, and this was extensively discussed in 2006, but the progress is enormous when it comes to sensitivity and resolution. But it also leads to that the complexity has really increased and we've seen that throughout these 5 days. There are large sample studies being performed, and we hope to see the interesting outcomes from these. the chemistry calculations now includes dust formation, gas dust chemistry, internal UV sources, effects of companions, effects of circumstellar structure. It's really getting more and more complicated. And it was really good to see this uncertainty study based on library reactions, so we get a feeling for how accurate things that we predict really are. And okay, and the chemistry calculations can then be compared with, in detail, really, with observationally estimated abundance distributions, and also in environments of different characteristics. So the super wind phase was really something that was discussed decades ago intensely. It's something that you never hear of today, really, the super wind phase. Does it exist or does it not exist? I don't know. But I think there is certainly now evidence for dramatic changes in the mass loss characteristic at the tip of the AGB, and it occurs on really short time scale. So having said all of this, I think many of the basic uncertainties remain today in the study of circumstellar envelope. I mean, dust, I mean, the formation, the composition, amorphous or crystalline, grain structure, processing in ISM, the optical properties, and so on. There are really lots of uncertainties here. And this points to a very important point, that both for chemistry calculation and for dust, the interdisciplinary approach is very important, where lab studies play a crucial role. And this should always be emphasized. We really rely on this, that people are willing to do this type of studies of smokes and so on. Also, the microstructure of the envelopes. I would say the 3D models now predict relatively clumpy structures, and they can calculate number of clumps ejected per year, clump mass distribution, and so on. And I think the observations confirm this, that mass loss is really occurs in clumps. But of course, over time, it appears like this produces overall spherical structure on at least for the higher mass loss rate objects. We also see these induced large coherent substructures, especially for the low mass loss rates objects. They appear to smoothen out a bit at the higher mass loss rates. So, and of course, this complicates things. We also have the thermodynamics of the circumstellar object, the kinetic temperature law. This is crucial for modeling molecular lines, but we haven't really made much progress here on the theory side to get a proper handle of that. And we all normally assume something. And then we have the 12CO abundance. I mean, which abundance to use for mass loss rate estimates? That can be discussed and is probably different in different environments and so on. Okay, continuing, we have the characterization of AGB stars in the Milky Way and other galaxies. And in 2006, this was really centered on LMC, SMC studies. Now in 2022, there is much progress, of course, because of Earth-based dedicated surveys, spaceborne instruments that weren't available at that time. We have the upcoming Vera Rubin telescope and so on. We can see dusty AGB stars now detectable out to, say, 20 megaparsec and so on. Of course, the distance is not the important thing. The important thing is that we can observe AGB star characteristics in a multitude of environments and put constraints on the evolution on them. But we can also use them as probes of galaxies and so on. The impression I got was that the dust production, at least for the C stars, appears efficient also at low metallicity. We have the results from the sextans A. And we had the search for very low metallicity AGB stars. It looks like an heroic effort, really, to do that. But of course, it's very interesting for looking at the IMF in the very early universe. Is it extremely top heavy, or do we also see the lower mass stars there? And we should remember it's not only galaxies that we detect with these new instruments. Also globular clusters can be seen to large distances. We saw the first results of what we can expect from the Vera Rubin telescopes and things like that when we were presented by the Gaia results on the Milky Way with 300,000 M stars and 4,000 C stars. I am not sure I got the figures right there, but and in this case they were used to study, among other things, the Milky Way structure. And of course, in the end, the final Gaia data project, the Vera C. Rubin telescope, so it will produce an overwhelming amount of results, in particular on time series. But I think when seeing all of this, I think it's important for the future that we strike a good balance between detailed studies of individual stars as well, because this is really very important. We've seen a number of interesting cases here, which provides us with very interesting information. And then we somehow have to bridge what we see for the individual objects, what we see from these magnificent surveys. And of course, also the detailed studies need time series observation, and this is not always to our advantage when it comes to TACs. So star formation histories, galactic chemical evolution, population synthesis model, this was really very well covered in 2006. And my impression is that it's a bit less covered this time, but we certainly saw, as one example, how AGB stars can be used for looking at star formation histories, for instance, in other galaxies. We saw a detailed chemical evolution model for the solar neighborhood. And we looked at something that related to the formation of the solar system, and I learned that the Earth is the body richest in stardust. I didn't know that. Okay. And then we come to the importance of companions. And this was, if you look in the 2006, it's not discussed at all, really. And so I would call it the pre-companion era, the almost nostalgic era, I have to say, when we lived in a happy world and everything was hunky-dory. And well, so it has really become a major theme now in 2025. It's very fascinating, but leads to a lot of complications. And I think we should avoid to fall in the magnetic field trap, as I call it. I mean, everything that we cannot explain must be due to a companion. I mean, we should be careful there. Now, I will not make any attempt to summarize all the situations when a companion could have an effect on observational characteristics or the evolution of an object or so on. And I mean, we've seen some beautiful results on symbiotics, for instance, so on. So we should also remember that AGB stars are companions themselves, often as white dwarfs. And we learned that even in objects that produce highly relativistic jets, we have AGB stars. And we will learn that these are for the impatient astronomer because so much happens on a short time scale. So we learned about various mechanisms for mass transfer. And we saw how simulations show large-scale coherent structures in the circumstellar envelopes, but also had a good warning that what we see in this respect is not always due to companions. There's ongoing work on how such structures in the envelopes will affect the CO line profile, for instance, and how this will add uncertainties to our estimated mass loss rate. I think I should rephrase that because, as was pointed out earlier here, I mean, we do measure the circumstellar material, so we do measure, to some extent, the actual material, the actual amount of material that leaves the star. It's just that if the star would have been alone, it may not have produced that mass loss rate. But we're not, seriously making an error in the mass loss rate itself. So, and it was shown that even substellar companions can have an effect of this. But in relation to these simulations, I think we really have to make sure that we have the physics right here in these simulations before we believe in how enhanced the mass loss really become if you have a companion. All right, and then we have the barium stars and the problem with the observed period eccentricity diagram. I'll come back to that. And then finally, this is the last one, I can assure, not the last slide, but the last theme. So these are the post-AGB evolution. And so this was covered to some extent in 2006, but it really mainly focused on the use of planetary nebulae as probes. And that's very different from this time. And now we go really for the rare objects. That if you go from red giants to asymptotic giants to post-AGB objects, you go down in abundance, in number density, significantly. I'm not sure if the figures are perfectly right, but I sense that we have two types of post-AGB system. The naked ones, I call them, the post-AGB binaries with main sequence companions identified, circumbinary disks, in Keplerian rotation, maybe, I don't know how many have been shown to have Keplerian rotation. A circumcompanion disk and jets. And then we have the obscured ones with very massive outflows. And here you still see it should be the AGB CSE remnant, I would say. And we have large bipolar outflow, we have equatorial density enhancement, etc., etc. And it's not quite clear to me why we have this dichotomy between these two various types, but I'll come back to that. And of course, there may be imposters here also. We have the post-RGB objects, which may add extra information. Now, if we start with the naked ones, once again, it was a relief to hear that among these, the single post-AGB objects are also important. And there are those objects. So the binaries we've seen, they are really excellent for studying binary disk interaction. But I think I understood that the eccentricity and period distributions of these objects are not the expected. I'm not sure if it is the same problem as for the barium stars, but okay. And I also find the similarities between protoplanet disks and post-AGB circumbinary disks very interesting and intriguing. And it, of course, leads to the thoughts of a new planet formation and so on. The circumbinary disks have been classified into full disk, transition disks, and faint disks. I'm not sure if these are chronologically related. I mean, do all objects go through these phases, or is it more complicated than that? And then, yeah, exactly. And then, of course, the unseen companion is seen as absorption lines through the circumcompanion disk wind. And this study really shows the importance of having dedicated instrument like the Mercator. I mean, this would never, ever fly otherwise through a time allocation committee on another type of telescope. And then this dust trapping leads to elemental depletions that eventually leads to peculiar stellar abundances in their atmosphere. It's an interesting phenomenon, which I gather is also not fully understood. In general, there are many unsolved problems. There was no way I had the ability to write them down, all of them, so you should see the presentation by Van Winkel. And we saw early this morning that there are some really peculiar objects like the red rectangle, which has a mixed chemistry, has a oxygen-rich chemistry and also a carbon-rich chemistry, and it apparently produces very large grains in its disk. And then we go to the massive ones, and these are really very complex objects. Well, I would say also the naked ones are very complex objects, and we saw this beautiful example of OH 231.8. And even if we don't see it, I think it's hard to think that binaries do not play a role here. And maybe even we need common envelope evolution to get a full understanding of these. And once again, here there were many open questions that I did not have time to write down. So I guide you to the presentation by Carmen. I would say chemistry is really a very good tool here because now you have an increase in UV flux and shocks and so on, and this will definitely alter the molecular setups and will lead to insights. And also the radio recombination lines are excellent probes of the emerging H2 region if you look at the objects that have evolved even a little bit longer. And one problem I see here is that the overall statistics for these objects is poor, and are we only looking at the extreme objects? And so we don't have really the full picture. And apparently new studies are underway. And I think it would be good to have a sort of a complete sample of sources and then see the frequency of different types of objects to really get a full understanding of this. And then we discuss evolution issues. When do the circumstellar disks appear? Their lifetime? When are jets formed? Precessing? Yeah, there's so many questions around here. Planetary nebula, hardly covered this time for some reason. Maybe they come back the next time if there is a next time. But I saw one poster on this. And also central star evolution was not really covered in this conference. I remember it was discussed quite a lot in 2006. And with that, I think I'll skip this one really. I think we've had enough now. So I go to the end. So will there be a sixth incarnation of the conference in 4 years or something like that? We'll see. That'd be interesting. So there's still a question mark on that. And then I think I would like to present some thanks at the end. I would like to thank the SOC. I'm a member. But a special thank really to Claudia, who took the lead in realizing this conference. Oh, okay. I wasn't finished there, but so what? Right. Yeah. Okay. Thank you. And then, as usual, a very special thanks to the LOC, because these are really the ones that made the whole arrangement work as smooth as possible. So maybe the LOC members can just stand up so we can thank them.
And
Hans,
yeah, I would like also, in behalf of the LOC and the SOC, to make some gifts to the chair of the SOC and the chair of the LOC. So please accept these gifts for up. Yes, this is for you. And
okay, and then my final thanks go to all of you, of course, for making it such an interesting and inspiring event. And I wish you a safe trip back to your home. Okay, thank you. I'm surprised that no one said that I made any errors in the slides. So, no, maybe you're too polite.
I think we now have some closing remarks from Claudia.
Yes. So you have one more presentation, I think, the last one. Well, before I get into that, or do we want to? Yeah, let's get into that. I just want to, I hope that you enjoyed Chile. and Santiago. For some of you, it was the first time. I want to invite you to come back, and especially to come back to visit us at ESO Chile. That we have different kind of programs. We have the visitor program. Now it's like there are 3 calls per year, and it is open to everyone, from PhD to senior astronomers. If you are a student and you want to come and spend some part of your PhD at ESO, you can do that via the studentship call, which is open twice per year. The fellowship in Garching is 3 years, in Chile is 3 years plus 1, and it's ESO VLT with paranal duties, and it's ESO ALMA. And we really want to have some application for ALMA coming from all around the world. We have also the internship for the master students, and overall there are also some dedicated Office for Science funds, so you can just contact some of the staff at ESO. So I really hope that, yes, take pictures of this slide and pass this also to the people in your institute. Okay. Then, the next slide, please. I also have some thank you to all of you, of course, again, for this very exciting conference with a lot of fantastic results and fruitful discussion. I found the program fantastic. I found the summary of the conference also fantastic. And Hans has been already informed that it's not yet over. We will write a messenger article about this. So keep an eye on the ESO webpage, it will come out. I also want to thank all the LOC members and the SOC. And for the LOC, I will really mention the names. It's Luciano, Ake, Martina, Julien, also the students that help us, the Ian, Pablo, Jaime, and Claudio and Daniel also. A special thank you to Paulina, Leslie, and Agnieszka from ESO, because they help us a lot with organization. And thanks for the funding to the ESO Office for Science and ALMA for the financial support, to CEPAL for hosting us, and the Modre for feeding us. And also to Chile Wine and Travel that helped us with the organization of both the excursion. I hope you enjoyed that. So. I take it as a yes then. You can find, if you come back to Chile, you can find them in Instagram. And then a special thank you to the IT colleagues that are up there. It has been a really great experience. I loved working with you. I hope that we come back. Okay, and then the next slide is the conference picture. And with this one, we will announce now the prizes. So you have all been very diligent and voted. The first one is the prize for the ALMA contribution.
Oi.
Surprise, surprise. We have it. And the prize goes to, I feel like at the Eurovision, Miora. Somebody takes a picture, please, Franz, for her work tracing the hotspot activity on Myra.
We should have had drums for this. Okay, so the next one is the prize for the best VLT contribution. And it goes to Julien Revon in the heart of Paiwan Gruis.
the prize for the best, it's Friday evening also for me, sorry. The prize for the best poster goes to Mats Esselders for orbital evolution of AGB binary systems. Quello giusto? Sì. Last one is for you.
The last one, which is the prize for the best student talk. And it goes to Ton de Prince, Interferometric Imaging Voyage to the Inner Rims of Dusty Post AGB.
Please, yeah, sorry, we take out this one. Yes.
Might as well.
Yes.
Sure.
So as you see, it was not so bad to be the last one as well. Okay, and with this one, we have one more final, very final announcement, which is, next slide. Ta-da! Well, put it in your calendar and hope to see all of you there. Thanks a lot.
I just want to say we will do our very best to not have it in exactly 3 years, because it would be cruel to have you come to Sweden in November. It will be nothing like Santiago in November. We will go back to the August tradition that the conference started with. That's much nicer in Sweden, yeah.
Thanks a lot to all of you. It has been fantastic to meet you again. See you soon.